GCE Advanced Level Chemistry Practical Series, experiment number 33. Experimental study of the characteristics of a dynamic equilibrium system using Fe3 plus and SCN minus system. So we are going to be using ferric ions and thiocyanate ions and establish an equilibrium with the use of those two ions. And the aim of this experiment is to develop a better understanding of a dynamic chemical equilibrium. So the type of equilibrium that is obtained over here is not a static one, it is a dynamic one, meaning there will be a forward and a reverse reaction happening at the same time. So students, we are going to develop a better understanding of a dynamic chemical equilibrium, an equilibrium that is established through the forward and the reverse reaction happening simultaneously at the same rate. And the second aim is to investigate the effect of application of some stress on equilibrium position of a equilibrium system. So we are going to investigate what happens when we apply some stress on equilibrium system. So these are the main two aims of our experiment. Important. So we are now moving on to some important details that are associated with this experiment. The coordination number of iron 3 is 6. So the coordination number in complex ions is the number of ligands that can directly be bonded to the central metal ion. So students, when it comes to forming complex ions, there will be metal ions bonded to different number of ligands. The number of ligands each metal ion is bonded to directly is referred to as its coordination number. So when it comes to Fe3 plus ions, when it comes to Mn2 plus ions, cobalt, nickel, copper, zinc, you can see their coordination numbers are listed below actually in this table. Now if you take something like metal ions that carry a 1 plus charge like Q plus ions, they usually have a coordination number of either 2 or 4. Usually they bond to 2 ligands or 4 ligands when forming complexes. When it comes to manganese, when it comes to Fe2 plus, cobalt 2 plus, nickel 2 plus, copper 2 plus and Mn2 plus. Now all of these are metal ions with 2 plus charge. Their coordination numbers are given here. So Mn2 plus can either bond to 4 ligands when forming certain complexes, or it can also bond to 6 ligands when it comes to forming different other complexes. Now Fe2 plus usually bond with 6 ligands. And then we have some, you can also see there are some other metal ions listed below like cobalt, nickel, copper, or in this case copper 2 plus, which is cupric ions, and zinc 2 plus. They all would form 4 or 6 bonds with 4 or 6 ligands. Over here we have M3 plus ions, or ions with 3 plus charge. So we have a few metal ions listed over here along with their coordination number. So students, going over these will give you an idea when it comes to forming different types of complexes, how many ligands they usually bond to. For example, when you take a look at scandium 3 plus, you would know that scandium 3 plus will not form a coordinate complex with just 2 ligands or with just 4 ligands. Usually when it comes to scandium, it will have 6 ligands bonded to it, right? So with this you can develop an idea about how many ligands will be bonded to each of these metal ions when they are forming complexes. An example of a coordination complex that Fe3 plus forms is given here. Actually, this is a complex ion that Fe3 plus forms. You can see over here with 6 water ligands. Now, water has a lone pair on oxygen. Actually, a water molecule has 2 lone pairs on oxygen, and 1 lone pair can be donated to form a dative covalent bond between oxygen and Fe3 plus. We say it's a coordinate bond. So, 6 water molecules can form these types of bonds with 1 Fe3 plus and form this complex ion, hexaaqua iron 3 ion. So, this particular complex ion, students, have 6 coordinate bonds. So, we say the coordination number of Fe over here is 6. There will be 6 water ligands forming bonds with 1 Fe3 plus. And as water molecules are considered neutral ligands, water molecules do not possess a charge, so therefore they are neutral. So since water molecules are neutral, when 6 water molecules are bonded to Fe3 plus, the ion that they form will have the charge that Fe3 plus had. So Fe3 plus had 3 positive charges, so the entire complex ion that is formed here will have a 3 plus charge. So this is one example. You can see the color as well. Now this aqueous complex has a yellowish color or yellow color. Reactions of hexaaqua iron 3 ion with a strong base. The yellow color FeH2O6 3 plus solution or hexaaqua iron 3 ion solution will form a red-brown precipitate. So this solution will form a red-brown color precipitate when added with a strong base. So as you can see over here, we have the complex ion present. When you add hydroxide ions or when you add sodium hydroxide, due to complete dissociation of sodium hydroxide in water, hydroxide ions will be added to water. So then hydroxide ions and these complex ions can react to form ferric hydroxide, FeOH thrice. So ferric hydroxide is a water insoluble red-brown color precipitate. Apart from that, 6 water ligands over here will be removed. So students, what you form here is the red-brown color ferric hydroxide precipitate. So if you add hydroxide ions to an aqueous Fe3 plus ion solution, the observation you make is the formation of a red-brown color precipitate. For a ferric ion solution, if you add sodium hydroxide, you can see the formation of a red-brown color precipitate. With aqueous ammonia, which is also a base, but not a strong base, a weak base, the yellow color hexaaqua iron 3 ion solution will form a red-brown color precipitate. Again, over here, this is our Fe3 plus ion solution. Whenever Fe3 plus ions are present in aqueous medium, we can assume that they are present as hexaaqua iron 3 ions. So when it comes to reacting these ions with ammonia, you can see since ammonia also can produce OH minus ions in aqueous medium, this will also result in forming our red-brown color precipitate. Ammonia will react with water and gain a proton while deprotonating water, meaning in a water molecule H plus will be removed and OH minus will be formed. So students, ammonia will turn into ammonium hydroxide. So ammonium ions and hydroxide ions will be introduced into the medium, and with the hydroxide ions we can form ferric hydroxide when Fe3 plus comes into contact with hydroxide ions. So ferric hydroxide, again, as I mentioned earlier, is a water insoluble red-brown color precipitate. Then we move on to the main oxidation states of iron. The electronic configuration of iron is given here, or Fe is given here. You can see Fe is having this electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, and according to Aufbau principle, we are filling 4s because 4s has less energy than 3d. So then we fill 3d. However, if you arrange them according to the distance from the nucleus, we see the outermost energy level is going to be 4s. So you can actually rearrange this the following way: 1s2, 2s2. When you're writing electronic configuration, even this second method that I'm showing is also correct. 2p6, 3s2, 3p6. So you can follow the Aufbau principle and fill electrons to 4s2. Then you can fill the remaining electrons to 3d. So even if you have written it like this, that is still a correct electronic configuration. You should know this by now. And afterwards, students, we do know that the fourth energy level is further away from the nucleus compared to the third. So when you're removing electrons, we are going to be removing electrons from the fourth energy level first. So in its outermost energy level, 2 electrons are present. So if you're talking about the outermost energy level of iron, you can see there are 2 electrons present. So the removal of these 2 electrons result in the formation of Fe2+ ions. When 2 electrons are removed, there will be 2 positive charges introduced into the ion. So therefore, what we form is Fe2+. The Fe2+ ion, however, will have this electronic configuration, right? The 4s electrons are now gone. So we have 3d6 here. So when you have 3d6, students, you should know when it comes to sub-energy levels, we can obtain stability when they are completely filled or when they are partially filled, or when they are completely empty also, there is another level of stability. Over here, this is not completely partially filled. It is actually having one paired set of electrons, while there are 4 other unpaired electrons. So if it is only partially filled, meaning if it only has unpaired electrons, at that point we can say that they have obtained a certain level of stability. So this is the situation you would observe when the d orbital is partially, or d sub-energy level is partially filled, but over here we have a pair of electrons. So this is not a stable electronic configuration. Considering the d sub-energy level, it contains 6 electrons. Achieving partial filling with 5 electrons is more stable than having 6 electrons. Thus, an additional electron is removed from Fe2+ to yield Fe3+. So students, we will remove this 1 electron over here. So this electron will be removed. So when you remove that electron, you will have only 5 electrons in the d sub-energy level, which is a stable electronic configuration. So at that point, the ion that is formed is Fe3+. So this electronic configuration happens to be more stable than the electronic configuration that is observed in Fe2+. So that is why you observe majority of the time, even when you prepare a Fe2+ ion solution, gradually it will turn to a more stable ion, which is Fe3+. The main oxidation numbers of iron is Fe2+ and Fe3+. Fe3+ being more stable. Now students, in this table we have the reactions that are usually associated with iron and the different oxidation states that can be seen when iron is undergoing these reactions. So first let's take a look at the reactions that are taking place. So over here we have iron solid, so that is the standard state of iron. So at that point students, the oxidation number is 0. So we usually take iron powder or iron solid for reactions in the lab. And when you carry out a reaction with iron solid and sulfuric acid or HCl, we can form Fe2+ ions in aqueous medium. So Fe2+ ions in aqueous medium will be present as this ferrous iron and water complex ion. So hexa-aqua iron 2 ions will be formed. So this particular ion complex is going to have a pale green color. It appears pale green in color. It appears pale green in color. And apart from that students, when you add sodium hydroxide to this, when you add sodium hydroxide to Fe2+, you will form ferrous hydroxide. So this is the full formula of the ferrous hydroxide that you form, right? FeOH2 H2O4. So this complex can be formed, and at that point the precipitate that is formed, this is a precipitate that is formed, that precipitate is going to have a darker green color, more unclear darker green color. We also refer to it as a dirty green color. So when you add hydroxide ions, that is the observation. So if you take Fe2+ ion solution and add hydroxide ions, you will see a darker green color precipitate formed, or we also refer to that precipitate's color as dirty green color. Apart from that, as you know, Fe2+ ions are less stable than Fe3+. So once you form or once you prepare Fe2+ ion solution, upon standing it will oxidize to form Fe3+. So Fe2+ gradually undergoes oxidation to form Fe3+. So students, Fe2+ ion solutions are going to be pale green in color, or Fe2+ ion solutions are pale green in color, but a pale green color solution gradually changes its color to turn to a yellow brown color solution. This is because Fe2+ gradually oxidizes to form Fe3+. So this is reversible. However, if you allow Fe2+ to stand in air, it will turn to Fe3+. If you add hydroxide ions to this Fe3+ ion solution, you will see the formation of a red-brown color precipitate due to formation of ferric hydroxide. So the formula is given there, FeOH thrice, H2O thrice as well. So again, we can see the coordination number here. Also the coordination number is 6. For Fe3+, the coordination number is 6. Over here also Fe2+, the coordination number is 6. There are altogether 6 ligands connected to Fe2+ as well as Fe3+. Now students, if you add an acid, you can again form this yellow brown color aqueous solution. Apart from that, if you take our yellow brown color solution over here, ferric ion solution, and add thiocyanate ions through the addition of a salt like sodium thiocyanate, sodium thiocyanate will dissociate and will introduce thiocyanate ions into the medium. So thiocyanate ions and ferric ions that are present in the medium in this particular complex will actually form this dark red color solution, not a precipitate. This is a solution that is formed. Iron 3 thiocyanate complex ion will be formed. So this particular complex ion that is formed with 1 thiocyanate ion and 5 water ligands along with Fe3+ is going to have a dark red color. It's a very prominent, intense red color. We also call it a blood red color. So it's a very intense dark red color that is formed when Fe3 plus ions are added with thiocyanate ions. We can see the formation of a very intense dark red color solution. This is not a precipitate. This is a solution that you form. So students, those are the observations you will have. So ferrous aqueous ion solutions, if you clearly indicate their colors over here, ferrous aqueous ion solution, they will have a very light green color. Ferric or ferrous hydroxide precipitate, will be a very dark green color. Actually, we do not have a dark enough green color to be shown here. However, we'll try and use a bit of a darker green color over here. Actually, the ferrous hydroxide precipitate's green color is much darker than this, and a bit of a unclear nature will be present, making it appear quite dark in color. So we say it's a dirty green color that you observe. Apart from that, we know this is a yellow brown color that you see, and we have a red brown color precipitate. So again, we have a yellow brown color solution. Think the best we can do is this color, and we will have a red brown precipitate formed. So with the given colors, this will be the color that comes closest to the color that we actually observe. So keep in mind, students, we are just using these colors to give you an idea, but the actual colors are not close to the colors that we have over here under our options. However, when it comes to this particular dark red or blood red color solution that is formed, it's going to be a very intense red color. It's a bit of a darker red. This is bright red. So the solution that is formed here, it's going to be a darker blood red sort of color. Right, students. So now we can move on to the next part. So over here, we can see a test that we can do to identify the presence of Fe3 plus ions. So whenever we have Fe3 plus ions in the medium, if you react Fe3 plus ions or Fe3 plus ion solution with thiocyanate ion solution, this will produce our iron 3 thiocyanate complex ion, which is going to be having this very intense or dark red color to it. So this red color is quite prominent, and this type of red color can only be formed when our thiocyanate ions react with Fe3 plus ions, if Fe3 plus ions are present in the medium. So we can use this test as an identification test for Fe3 plus ions. As indicated above, the yellow brown color solution will turn to a dark red color solution upon addition of thiocyanate ions. And the coordination number over here is 6. The coordination number over here is 6. You can see with one Fe3 plus ion, there are 6 water ligands attached to it. So therefore, the coordination number over here is 6. Even in this complex ion, you can see there are altogether 6 ligands, 1 thiocyanate ion and 5 water ligands are forming coordinate bonds with Fe3 plus. So how many coordinate bonds are present around Fe3 plus? Altogether 6. That is why we say coordination number over here is also 6. So in both of these cases, the coordination number of Fe3 plus is going to be 6. The complex Fe3 plus ions form with thiocyanate ion is dark red in color. This reaction can be used as an identification test for Fe3 plus ions. Due to its unique color, we can actually, and unique color change, we can actually use this as an identification test for Fe3 plus ions. Behavior of Fe3 plus ions in water. So, Fe3 plus ions in aqueous medium will form this hexa-aqua ion 3 ion complex. Later, they will undergo deprotonation to form the following equilibrium. So, Fe3 plus ion is somewhat of a small ion and it has a large charge, right? A small ion with a large charge. So, it attracts electrons quite strongly towards itself. So, this can cause a deprotonation in water ligands that are added or that are forming bonds with the Fe3 plus ions. So, water ligands that are bonded to Fe3 plus can undergo deprotonation due to the reason I mentioned earlier. So, when that happens, students, you can see you can form this FeOH H2O5 complex. The overall charge of the complex is +2. Why now? Because we have formed hydroxide ion which will have 1 minus charged. So, Fe is 3 plus, 1 minus charged hydroxide ion is here. So, the overall charge is 3 minus 1, which is going to be 2 plus. And due to the deprotonation of one water molecule, there will be an H plus removed. One hydrogen ion or H plus ion will be removed. So, this complex that is formed is the complex that is yellow in color. So, now we know the complex that is actually producing the yellow color in a Fe3 plus ion solution. Fe3 plus ions in aqueous medium initially forms hexa-aqua ion 3 ion. You can see over here. That means Fe3 plus ions first will connect with 6 water ligands and form a complex ion. And actually that ion will have this pale purple color. It's a very light color, or the color intensity of this complex or this particular pale purple color is very low, so you will observe it to be colorless. However, this complex will not stay in the aqueous medium for much longer, because as it gets formed, an equilibrium will be obtained or established. So at that point, what happens is this complex will turn into this particular complex where one water molecule will undergo deprotonation, forming a hydroxide ion. So you can see with one Fe, there's going to be one ferric ion, there's going to be one hydroxide ion along with 5 water molecules. So this complex is yellow in color. Apart from that, even that complex can undergo another deprotonation to form this Fe. We have to close the bracket here. So we have FeOH twice, H2O 4 times plus 1. So we can see another H plus is removed. Another H plus is removed. So this is still an aqueous solution, right? So we can see there are 2 hydroxide ions bonded to Fe3 plus, and this is a yellow color solution. So when you observe that Fe3 plus ion solutions are yellow brown or yellow color in medium, that is because this complex has been formed in the aqueous medium. If it is purely this complex that is present in aqueous medium, where one Fe is forming coordinate bonds with 6 water molecules, at that point the color would be pale purple, or you will observe it to be colorless, because the color intensity that is mentioned here of this particular color is very low. So therefore you will observe it to be colorless. However, this complex will not be present in water in high concentrations. As this equilibrium is established, you will form more of Fe3+ forming coordinate bonds with hydroxide ions through deprotonation of water ligands. So you can form this as well as this complex in aqueous medium, which will turn the aqueous medium into a yellow color. Apart from that, there's another important detail you have to keep in mind. So apart from the yellow color that is present here, that is coming through these two complexes, you can see when these complexes got formed by pulling electrons more towards the Fe3+ ion and leaving one of the hydrogens vulnerable for breaking away and forming H+ from the water molecule. When H+ is formed that way, the H+ ion concentration in the medium will go up. H+ ion concentration in the medium will go up. So through these equilibriums, we will introduce more and more H+ into the aqueous medium. This is why there is a little bit of a higher H+ concentration in a Fe3+ aqueous ion solution. Usually, students, we say ferric ion solutions are slightly acidic. According to the above equilibrium, aqueous solutions of Fe3+ ions are acidic in nature, right? Why? Because as this equilibrium gets established, you can see H+ ions are released into the aqueous medium, right? So apart from the color that you observe, one of the other very important things to keep in mind is the H+ ions that are released will contribute to increase in the high H+ concentration in the aqueous medium, making the medium acidic. So ferric ion solutions are acidic in nature. When dilute acid is added to the above equilibrium, the H+ concentration will go up. Yes, when we add acid also into the medium, H+ ion concentration will go up. So therefore, according to the Le Chatelier's principle, the above two equilibrium reactions will have their equilibrium position shifted to the left, producing more and more FeH2O6 which will turn the solutions pale purple or colorless. So again, if we revisit over here, if I increase the H+ concentration of each of these solutions, actually these equilibriums are existing in the same solution. So if I add acid to this solution, then what happens? I have externally influenced the equilibrium system by adding H+. So I have externally increased the H+ concentration. So Le Chatelier's principle states, when we try to influence the system by stressing the system by changing the concentration, pressure or the temperature, the system will adjust itself to minimize the change that has been done. So when you increase the concentration of H+, the system will try to decrease the concentration of H+ by carrying out the appropriate reaction. So over here, when we increase the H+ concentration, the equilibrium system will try to bring down the H+ concentration by utilizing it more, by favoring the reverse reaction more. That means until a new equilibrium is established, the reverse reaction will be favored more. That means H+ is going to be used up and will be removed from the system more, according to Le Chatelier's principle, meaning the reverse reaction will happen more. So when the reverse reaction happens more, what other product gets produced more? This particular complex ion will get produced more. So this FeH2O6 ion concentration will go up. H+ ion concentration goes down. So when H+ ion concentration goes down, along with it, these concentrations will also go down. So we'll note that down. So this will go down. Along with it, both of these concentrations will also go down, which will contribute to increasing. In this case, yes, this will increase, but that will be countered by the reduction of the same ions concentration here. Apart from that, this FeH2O6 Fe3+ ion concentration will increase. So that is something that we have to keep in mind, students. When we increase the H plus concentration by adding a strong acid, you will see this yellow color in the medium will decrease, and you will see the solution is turning more or less colorless. It could also give off a pale purple color if hexaquine 3 complex is going to be present in adequate amounts in water. Note: hexaquine 3 ion solutions are pale purple in color. However, dilute solutions of these ions will appear colorless. Yes, this pale purple color is not a very intense color. It is a very light color, which is very difficult to observe in lower concentrations of this complex. So at higher concentrations of this complex, at that point you will be able to observe this color faintly. However, at lower concentrations, due to very low color intensity of this particular complex ion, you will not be able to observe this color. Instead, you will observe that the solution is colorless. Dissolving ferric ions in sulfuric acid. So you can take a small amount of solid ammonium ferric sulfate and add dilute sulfuric acid. At that point, you will initially form a colorless solution, because as you see here, there are ferric ions and you are adding sulfuric acid. So basically, students, the medium that is going to be formed over here is going to be quite acidic. So as you know, in quite acidic medium, you will see the formation of our Fe3+ 6 water ligand complex ion, which is hexa aqua ion 3 complex ion. So that is going to be appearing colorless here. So this is the complex ion that is going to be formed, and that is going to be a colorless solution. And the coordinate number or coordination number there also is 6, something to note. Apart from that, after carrying out this experiment, if you carry out a similar experiment by taking solid ammonium ferric sulfate and add water instead of adding the sulfuric acid. Now, sulfuric acid is strong acid, and we are adding, we can add concentrated sulfuric acid if you want, right? If you really want to observe this colorless solution, for sure you can do that, but even dilute sulfuric acid will be sufficient enough. So we have enough and more of H plus concentration here to shift the equilibrium that we spoke about earlier to the left to produce more of this. So instead of reaction going forward, producing more and more of these two ions, when we increase the H plus concentration, what happens is, to bring down the H plus concentration, the reaction will be favored towards the left hand side, producing more and more of this pale purple color hexaqua ion 3 complex, hexaqua ion 3 ion complex. So because of that, students, when we dissolve this ferric salt in acidic medium, the solution that is produced will appear colorless. And as you know, ammonium ions and sulfate ions, they don't also have a color, so they will not interfere with the process. But if you add water to this ferric ammonium sulfate, at that point, students, here there are no H pluses additionally coming into the medium. You are adding just water. So at that point, usual equilibrium that we stated in a previous slide will be established, where first hexaqua ion 3 complex will be formed, right? Hexaqua ion 3 ion complex will be formed, and after that, due to deprotonation, you will have certain hydroxide ligands formed, which is going to be bonded to Fe3+ ions. So along with some water ligands, there will be certain number of hydroxide ligands. Hydroxide ligand number could vary from 1 or 2. If it becomes 3, then at that point you will see the formation of ferric hydroxide precipitate, right? But if the hydroxide ion number is limited to either 1 or 2, at that point the solution that is formed is going to appear yellow in color. So this complex can form when you add just water, and due to deprotonation of some water molecules here, the medium, the solution that is formed, is going to be acidic. That is also another observation we should make. So if you take a portion of this solution and test it for acidity, you will observe that it is going to be slightly acidic. So why did it become acidic? Because when the hexaaqua iron 3 ion complex was turning into the complex that is given over here, a deprotonation of water molecules took place. That means H plus was removed from water. So this removed H plus come into the aqueous medium, making the medium acidic. So what happens when we add Fe3 plus ions with thiocyanate ions? Now Fe3 plus ions, as we know in aqueous medium, will appear yellow, right? That is the usual color you will observe, because we don't always dissolve Fe3 plus in dilute sulfuric acid. We will dissolve ferric salts in water. So this will result in the formation of a yellowish solution, yellow brown or yellowish solution. So when we add thiocyanate ion solutions are colorless. So you can take a potassium thiocyanate or sodium thiocyanate. When you add it to water, they will dissociate to form the metal ion or sodium ion and thiocyanate ion separately. So these ions are now present in aqueous medium. So if you take a portion of that solution and add it to a ferric ion solution, immediately you can observe the formation of this really dark red color solution. Really dark red color solution. So iron 3 thiocyanate complex will be formed here. And this particular ion, complex ion, will be formed here. So this complex ion will have this intense red color. And the forward reaction happens to be a reaction that is having an enthalpy change which is negative, meaning the forward reaction is going to be exothermic. The balanced chemical equation between Fe3 plus aqueous solution and thiocyanate ions are given here. So although we have written it like a unidirectional reaction, this is actually an equilibrium reaction. You will note this as we discuss more details about this reaction. But for the time being, we'll observe if you add sufficient number of thiocyanate ions, you can see directly the formation of this complex that we have written down over here. So Fe would form a complex with 5 water ligands and 1 thiocyanate ion. So we can also call this ion pentaaqua thiocyanate 2 iron 3 ion. Right, so this particular ion that is formed here, students, is going to be dark red in color. Very important detail. Apart from that, the hydroxide ion over here will be removed. Instead, the thiocyanate ion will take its place. So this is the reaction that you can observe. But keep in mind, as I mentioned earlier, this is a reversible reaction. You will observe that later down the line. So now we are getting introduction to what we are mainly about to do in this experiment. It is possible to shift the equilibrium in a desired direction by applying a stress to the system. This process is explained by Le Chatelier's principle, which states that when a system at equilibrium is subjected to a stress, the system will react so as to relieve the stress. Now, we are also like that. When you are applied with a certain amount of stress, you will work hard to come out of that stress or relieve that stress. Similarly, when we apply a specific stress to a system, by the changing of concentration of reactants or products, by changing the temperature, especially when it comes to gaseous systems, if you change the pressure. So these are different types of stresses that we can introduce into an equilibrium system. So when you introduce different types of stresses to an equilibrium system, the equilibrium system will adjust itself to relieve or minimize the change or the stress that has been put on it, right? So he states that the system will react so as to relieve the stress. Some examples of stresses that can be applied to an equilibrium system are changes in concentration, both increasing and decreasing of reactants and products concentration. Pressure is applicable for systems involving gases. And temperature is applicable for an equilibrium. Note, changing concentration of reactants and or products will never change the equilibrium constant of a reaction. So we know equilibrium constant Kc, or for a gaseous equilibrium we can also talk about Kp. So these types of equilibrium constants will only change with temperature. They will never change when we change the concentration or pressure. They will only change if you change the temperature of an equilibrium system. At a given temperature, the equilibrium constant values will not change. Even if you change the reactant concentration or product concentration, at a given temperature, the equilibrium constant values will not change. In this experiment, the effects of change in concentration will be observed. Yes, our main task in this particular experiment is to observe how changing the concentration of reactants will affect the equilibrium, whether the equilibrium constant is going to change or not, or what type of shift will take place in the equilibrium position of the equilibrium. Developing an understanding about chemical equilibrium. Take approximately 2 cubic centimeters of ferric iron solution to a test tube and add few drops of sodium thiocyanate solution. Sodium thiocyanate solution will be added to ferric iron solution. So you can see for 2 cubic centimeters we only add few drops of sodium thiocyanate. Why? Because in the presence of even this few drops of sodium thiocyanate, there will be a very dark red color formed, right? So we don't want the solution to be too dark. So then when we are trying to manipulate the equilibrium system, we will not easily observe the color changes that take place with addition of small volumes of other reagents. You will have to add large volumes of other reagents to see a color change. So we don't want to go in that direction. We will add only a few drops of sodium thiocyanate. Even that will produce a really dark red color in the medium. So after this, when this solution is diluted with distilled water, a solution with a lighter red color, close to the color of tea, will be formed. So when you add distilled water to this 2 cubic centimeters of this really dark red color solution, you can actually see by diluting it by addition of distilled water, you get to a lighter red color, closer to the color of just plain tea, right? You might have seen the color of brewed plain tea, which is going to be transparent, but it has a very clear but somewhat of a dark red color, right? But that red color is lighter than the initial red color you observe in the medium when we were initially forming this complex. The solution formed above has the equilibrium shown below. So this particular equilibrium exists in the solution we have prepared now, right? There is ferric ions in the medium, thiocyanate ions in the medium, and the ferric thiocyanate complex will also be present in the medium. That is why the medium is red color. Right, so this equilibrium will exist. Now you might also observe, due to the presence of ferric ions in the medium should be yellow color, right? However, students, keep in mind that due to the very intense red color of this particular complex that we have over here, complex ion we have over here, even if there are few moles of few Fe3+ ions in the medium, we do not observe the yellow color because yellow color will be masked with this very intense red color. So students, this equilibrium will exist in the solution we have already formed. And using that solution, in the above equilibrium, both forward and the reverse reaction take place when an equilibrium is established. The forward reaction rate will be equal to the reverse reaction rate. So that is another thing that you need to keep in mind. In this particular equilibrium, if the equilibrium is established, that means if they have obtained an equilibrium, at that point the forward reaction rate and the reverse reaction rate are both going to be happening at the same rate, right? The forward reactions rate will be equal to the reverse reaction rate. So that means if a number of reactant particles turned into products, simultaneously the same amount of products will replace the number of reactant particles that got used up. So at that point, when the equilibrium is established, whatever the concentrations of reactants will not change, as well as the concentration of the products will also not change. If forward reaction rate is Rf, the reverse reaction rate is Rb, or backward reactions rate is Rb. So at equilibrium, Rf will be equal to Rb. Since Rf is equal to Rb at equilibrium, the concentration of reactants and products will not change after obtaining the equilibrium. So the concentration of reactants and products, will not change after the obtaining of the equilibrium. So you can see how concentration of each of the reactants and products change over time when we allow this equilibrium to be established. So we'll read this text that is given here first. According to the above graph, the system has reached an equilibrium at time t. So over here we have time t. So at this particular time, we can see we have obtained equilibrium. So how do we know by looking at the graph that we have obtained equilibrium at that point? Do you see, when it comes to ferric ion concentration and thiocyanate ion concentration, we have started at a higher concentration values in the beginning. And ferric thiocyanate complex ion concentration is 0 at the beginning. But as we allow these two reactants to react with one another, their concentrations go down because they will get used up to form the product. Product is the ferric thiocyanate complex ion. So the complex ion will get formed more and more. At that point, since we now have more and more complex ion, the complex ion's rate will also go up. Over here what we see is the concentration, not the rate. So you can see as time passes by, the concentration of the complex ion goes up, and as time passes by, since the reactants are getting used up, their concentrations dwindle, their concentrations will go down. At one point, students, you can see the concentrations of the reactants are these two, and products do not change. So from time t onwards, no matter how long you allow the system to go on doing this reaction, you will see the concentration of the product or the reactants will not change after that time. Even if you allow it to stay in the same medium for about an hour or so, you can see the reaction will not change the concentration of the reactants or the products. So at that point, we can observe we have obtained an equilibrium. We say at this time t, we have established and equilibrium. So this means from T onwards, the concentration at Fe3 plus, concentrations of Fe3 plus and thiocyanate ions and ferric thiocyanate ion complex remains unchanged. This is because due to obtaining a dynamic chemical equilibrium, the forward and the reverse reaction rates are the same. So students, as we saw earlier, the concentration of the reactants initially are high. We have high concentration. And then as time passes by, since the reactants are getting used up, the reactant concentrations come down. So if you compare these two instances, initially, since the reactant concentrations are high, the rates of the reactions, forward reaction, will be high. As you know, the concentration of reactants are going to influence the rate of the reaction. So if the reactant concentrations are high, the rate of the reaction will be also high. So in the beginning of this reaction, we had no product concentration, but the reactant concentrations were high. So at that point, the forward reaction rate is high. But as the forward reaction happens, the reactant concentrations come down. So then what happens? When the reactant concentrations are lowered, at that point, what will happen to the forward reaction rate? If the reactant concentrations are low, forward reaction rate will also be lowered. So as time goes on, you can see the reactant concentrations are going down. That means if I roughly draw over here the rate related graph, time, and over here it will be the reaction rate. The forward reaction rate initially will be high, but gradually it will come down. When it comes to the reverse reaction, right, we will take our product thiocyanate as the main reactant that will regulate the reverse reaction rate. So you can see when you talk about the reverse reaction, if the concentration of the products are high, the reverse reaction rate will be high. But at the beginning, this particular product will not be there. So since there is no product, there is no reverse reaction. So that means there's no rate for the reverse reaction. But as the forward reaction happens, the forward reaction happens, the product concentration will go up, which will gradually increase the reverse reactions rate. So you can see over here the product concentration gradually increases, which means when the product concentration goes up, the reverse reactions rate will also go up, because reverse reaction rate will depend on the concentration of this ferric thiocyanate ion complex. So when this particular ion complex gets formed more and more, the reverse reaction rate will increase. So this is our forward reaction rate. Reverse reaction rate initially, since the concentration of the ferric thiocyanate ion complex is less, actually zero. In the initial situation it's zero. So therefore, reverse reaction rate starts from zero, but it will gradually increase, and at one point, the reverse and the forward reaction rates will be equal to one another at one point. From that point onwards, when the reverse and the forward reaction rates are equal to one another, there can't be a change in the concentration of either the products or the reactants. So when I say these rates are equal, that means at the same speed, when the forward reaction is turning reactants into products, using the same speed, products are turned into reactants. So when these two are happening simultaneously, there will be no reduction in reactant concentration or no increase in reaction concentration as well. So at this point we can say we have obtained an equilibrium. The point at which we obtain this situation where the forward and the reverse reaction rates are the same is referred to as the equilibrium, or referred as a point at which we have obtained equilibrium. All right. So now we have the diagram that I drew earlier in this slide. So earlier we could compare the increase of concentration of the product leading to the increase of the reverse reaction, decrease of the concentration of the reactants was associated with the decrease of the forward reaction. So now we have developed an idea about what is happening. So we can dive into just the rate related graph over here. So over here the same things I mentioned earlier is given, right? So you can observe over here that when we carry out this reaction, forward reaction rate decreases like I mentioned earlier, and the reverse reaction rate gradually starts to increase. Starting from 0, it will gradually start to increase, right? So it will gradually start to increase this way. So forward and the reverse reaction rates will be equal to one another at time t. At this particular point, we have developed or we have obtained our equilibrium. At time 0, the thiocyanate and ferric ion concentration are high. Therefore, the initial reaction rate is high. Yes, again in the previous graph also we observed that these ion concentrations are high, so therefore initial rate of the forward reaction is high. However, as the reaction proceeds, the reactant concentrations will decrease. Due to this, with time, the forward reaction rate will gradually decrease. We have observed that earlier. At time t equals 0, there are no ferric thiocyanate complex ions in the medium. However, with time, this ion concentration will gradually increase, which will lead to the increase of the reverse reaction rate. So we are starting from 0, right? So reverse reaction rate will be 0 initially at t equals 0, because when we are starting this reaction, we didn't have any ferric thiocyanate ion complex in the medium. Only Fe3+ and thiocyanate ions were added to the medium. So there were no product concentration in the medium. So at time equals 0, t equals 0, there was no reverse reaction taking place. So therefore, reverse reaction rate at that point was 0. At one point, the forward reaction rate and the reverse reaction rate will be equal to one another. At this point, it is said that the system has reached dynamic equilibrium. Also, we say system has established a dynamic equilibrium. Equilibrium constant Kc. So students, when you are given an equilibrium reaction, you have to first observe whether the equilibrium reaction that is given to you is balanced. Afterwards, you can proceed to writing the equilibrium constant for that equilibrium given to you. So over here, when you're writing Kc, we have to first take a look at the product concentration, and we have to take the product concentration raised to the power of its respective stoichiometric coefficient divided by reactant concentrations raised to the power of their respective stoichiometric coefficients. So we have written the product concentrations divided by reactant concentrations, and each of these concentrations are raised to the power of their respective coefficient. So respective stoichiometric coefficient means the number that is written in front of each of these complex ions or each of these products and reactants. So the number that goes in front of each of these reactants and products is basically their stoichiometric coefficient, right? So you have to take those stoichiometric coefficients and write them as powers when you are taking each of these concentrations into account. So when you're writing the Kc value, you will first write the product concentration and whatever the number that is written in front of the product when you are taking a look at the equilibrium equation. If there is a number 2 over here, then this concentration will be raised to the power 2. However, there is no 2 over here, there's just 1. That means the power over here is 1, and over here as well in each of these reactants the power is 1. But we do not usually indicate the power 1 when this stoichiometric coefficient is just 1. We do not indicate the power 1. But if it is anything greater than 1, at that point we will have to very clearly write the powers associated with each of the concentrations given. So we will remove these powers. Changing the concentration of reactants and products will not change the Kc value. We have to very clearly understand this. Changing the concentration of reactants and products will not change the Kc value. Only temperature will change the Kc value. It will not get altered when we change the concentration of reactants or products. Let's move on to the next slide. Demonstrating the effect of concentration on equilibrium position. So this is the main purpose of our experiment today. So over here, we will be taking a ferric ion solution and be adding thiocyanate ions to it, and we will be forming this ferric thiocyanate ions or complex ions that are formed here, which will have this dark red color. And as you can see, the forward reaction is exothermic, or delta H is going to be minus. And after forming this solution, we are going to add distilled water and obtain a lighter red color solution. We say this solution should have a color that resembles plain tea color of plain tea. So once you have obtained a solution that have this lighter red color, we can proceed with the experiment. To observe how the equilibrium position changes with concentration of reactants and products, we can add different reagents to the system and observe the color changes. So we are going to add different reagents to this particular equilibrium, and if we add different reagents to this, we are going to stress the equilibrium out. Sometimes when you add excess Fe3+ ions and increase the concentration of Fe3+, then at that point, to relieve the stress, the forward reaction will be favored, producing more of this complex ion. If you remove Fe3+ ions, then again the equilibrium will be stressed. To produce more and more Fe3+ ions, the equilibrium position will be shifted to the left, or we can say the reverse reaction will be favored. If you add more of thiocyanate ions, then again equilibrium will be stressed due to us influencing the equilibrium system. So when we increase the thiocyanate ions, the forward reaction will be favored. So you know these changes that could take place according to Le-Chatelier's principle already. So let's observe how we can carry out this experiment. The initial color of the equilibrium system is a red color that is similar to the color of tea. Actually, it will be similar to the color of plain tea. Just when you take tea and brew it, the color of the plain tea that you produce is going to resemble the color of this ion solution. So it's a lighter red color. With the addition of suitable reagents, we can shift the equilibrium position. This can be observed with the color changes. So when we shift the equilibrium position, we can observe the shift of the equilibrium position with the color changes. For example, we will start with an equilibrium where the color is lighter red. But imagine we increase the Fe3+ ion concentration. So as the Fe3+ ion concentration is increased externally like that, the system will try to relieve that stress by decreasing the Fe3+ concentration. So that means the forward reaction is going to be favored. So when the forward reaction is favored, students, the concentration of this ferric thiocyanate ions will increase, right? When the forward reaction is favored, or when the equilibrium position is shifted to the right, due to the forward reaction being favored, this ion concentration will increase. Due to that, the dark color of the solution or dark red color of the solution will increase. So when this happens, we can very clearly notice this color change in the medium. Lighter red color will turn into a darker red color solution. The lighter red color of the solution will turn to a darker red color as we add Fe3 plus into the medium. If the equilibrium shifts to the right, as I explained earlier, if the equilibrium position shifts to the right, the medium will appear a dark red. If the equilibrium position shifts to the left, the solution turns pale yellow. Actually, the red color will reduce and the pale yellow color in the medium will increase. Changing the equilibrium position of an equilibrium system, we'll be using test tubes and we'll be using these chemicals, right? The chemicals that are given here will be used. 0.05 moles per decimeter cube iron 3 nitrate. We also say ferric nitrate. We can use ferric chloride as well. But when you're using ferric chloride, we'll be using ferric chloride in 0.05 moles per decimeter cube nitric acid solution. So we'll be using 100 cubic centimeters of 0.005 moles per decimeter cube potassium thiocyanate or sodium thiocyanate or ammonium thiocyanate solution. So we can use either one of these salts because each of them has the required thiocyanate ion that we want for this experiment. So we can use potassium thiocyanate, sodium thiocyanate or ammonium thiocyanate. We have to use sodium hydroxide, or we can use solid ferric nitrate or ferric chloride and solid potassium thiocyanate as well in this experiment. Method: take 5 cubic centimeters of ferric ion solution and add 5 cubic centimeters of thiocyanate ion solution. Now keep in mind, students, the thiocyanate ion solution had a very low concentration, right? So about 10 times less than this, about 10 times less than this. So because of that, students, we can take them in equal volumes, because although we add not just a few drops, 5 cubic centimeters of thiocyanate solution, the concentration of the thiocyanate solution is extremely low. So at that point, we will see a dark red color solution forming, and we will add distilled water to this and further dilute the solution to obtain the color we want. So this solution formed can be taken as the equilibrium system between Fe3 plus or ferric and thiocyanate ions. So you can see this equilibrium system is present in this particular solution, ferric ions and thiocyanate ions. Alright, so then you can see when they react together, we have the product form, the iron 3 thiocyanate complex ion. So apart from that, these ions are still present in the medium as well, since this is a equilibrium. The above solution is taken into few test tubes. So we will separate that solution into few test tubes so that we can carry out a few different tests with it. So the color of this solution is going to resemble the color of plain tea or tea that is brewed freshly. So this particular color is the color we want. Then the first test, decreasing the Fe3 plus concentration by addition of sodium hydroxide. So if you add sodium hydroxide to the medium, you can see that when sodium hydroxide is added, Fe3 plus ions in the medium, as we mentioned earlier in the theory parts of this experiment, Fe3 plus in the presence of hydroxide ions will get precipitated as a red-brown color precipitate, which is ferric hydroxide. So ferric hydroxide will be formed. So we are only adding a few drops of sodium hydroxide. That means not all the Fe ions in the medium get used up this way. However, due to the removal of Fe ions in the medium, due to the formation of ferric hydroxide, the concentration of free Fe3 plus ions in the medium will decrease. So now we saw that there is an equilibrium here, right? In this equilibrium, we are decreasing the Fe3 plus ion concentration by removing them from the medium by adding sodium hydroxide. So Fe3 plus ions concentration will drop or decrease, which will favor the reverse reaction. According to Le Chatelier's principle, if the concentration of one reactant drops or if the concentration of one reactant is decreased, the equilibrium system will adjust to relieve this stress, or equilibrium system will obtain a new equilibrium which will try to reduce the change or minimize the change that has been done to the system. Meaning, we are going to try and produce more and more of Fe3 plus ions in the medium to minimize the effect that reducing the Fe3 plus had in the medium. So the reverse reaction will be favored. So favoring the reverse reaction, meaning the reverse reaction will happen more and more. Therefore, the equilibrium position will shift to the left. Equilibrium position will shift to the left. So at that point, the concentration of this ferric thiocyanate complex ion will go down as the reverse reaction is favored. That means the reverse reaction is happening more and more until a new equilibrium is obtained. So therefore, the concentration of Fe3+SCN 2 plus ion will drop, meaning the dark red color that we observe here will gradually decrease, and since Fe3 plus ion solution is going to increase, it will start showing a bit of a yellow color in the medium. So that is what we have over here. When sodium hydroxide is added, the color intensity of the solution will decrease. This means the ferric thiocyanate complex ion concentration has decreased. Therefore, it can be concluded that the reverse reaction was favored. So this dark red color will decrease and solution will start to be more and more yellowish in nature. You will not observe a very prominent yellow color like this, but you can very clearly observe the red color of the medium decreasing and the yellowish nature of the medium increases. Apart from that, you can observe the precipitated ferric hydroxide solid over here. So ferric hydroxide solid will appear here as a red-brown precipitate. Right. So what happens first when you add ferric ions with sodium hydroxide is the formation of ferric hydroxide solid and sodium 1 plus ions. And the reaction that is given here, students, should be written as a equilibrium reaction. So we have to keep that in mind. This is not just a forward reaction, it is a equilibrium reaction. Both the forward and the reverse reactions are taking place still. When sodium hydroxide is added, Fe3 plus ions will precipitate as ferric hydroxide, red-brown color precipitate. Due to the reduction of concentration of Fe3 plus ions in the reverse reaction will be favored according to Le Chatelier's principle. Right, as I mentioned earlier, Fe3 plus ions and concentration goes down. Due to that, the reverse reaction will be favored according to the Le Chatelier's principle. Due to this, equilibrium position has shifted to the left when sodium hydroxide is added to the medium. So we can conclude, upon addition of sodium hydroxide, since the color of the medium decreased, the red color of the medium decreased, we can say the equilibrium position has shifted to the left, right? So if the equilibrium position shifts to the right, the equilibrium system will be more and more dark red in color. If the equilibrium position shifts to the left, the medium will be less red in color, or the color intensity of the red color in the equilibrium system will go down, and equilibrium system might also appear more yellowish in color. So in this case, we can see the color of the medium, red color of the medium has decreased, indicating the equilibrium position has shifted to the left. So we can conclude, upon addition of sodium hydroxide, equilibrium position shifts to the left. The reason for this is, as sodium hydroxide is added, it reacts with ferric ions to form ferric hydroxide precipitate. So therefore, ferric ions will effectively be removed from the system, which will cause the ferric ion concentrations to go down. So according to Le-Chatelier's principle, system will try to produce more and more Fe3+ ions. In order to do that, the reverse reaction should be favored. When the reverse reaction is favored, equilibrium position will be shifted to the left. Test addition of solid ferric nitrate or ferric nitrate solution to increase Fe3+ ion concentration. So if you add ferric nitrate or ferric nitrate solid or ferric nitrate solution into the medium, then what happens? Ferric nitrate will dissolve. If you add solid, ferric nitrate will dissolve in the medium and release Fe3+ ions and nitrate ions. Nitrate ions have no color and they do not interfere with the equilibrium. Fe3+ ions, however, will come into the medium and contribute to increasing the overall Fe3+ ion concentration. So when that happens, students, so over here, the Fe3+ ion concentration will increase. This will increase. When that happens, the forward reaction will be favored according to the Le-Chatelier's principle, right? We know when the Fe, or when one of the reactant concentrations are increased, now this is a stress on the system, so the system will try to relieve this stress. So in order to relieve the stress, the concentration of Fe3+ should be brought down. In order to do that, the forward reaction should be favored. So that means the more and more forward reaction will take place until a new equilibrium will be obtained. So that means the forward reaction rate will temporarily be greater than the reverse reaction rate. But at one point, the rates will be equal to one another. But at that point, the concentration of the ferric thiocyanate complex ion would have been increased compared to the initial equilibrium. So therefore, we can see a darker red color after the equilibrium position has gotten shifted to the right due to favoring of the forward reaction, right? So if I go step by step, Fe3+ concentration increases when we add ferric nitrate, and due to this, according to Le-Chatelier's principle, the system will try to relieve itself of this particular stress by carrying out a reaction that will reduce the Fe3+ concentration. So forward reaction is the one that should be done to reduce the Fe3+ concentration. That means the forward reaction is going to be favored. Favoring the forward reaction means that equilibrium position is shifting to the right hand side. And when that happens, you will see that the ferric and thiocyanate complex ion concentration will go up. So when that ion concentration increases, when this ion concentration increases, you can see that the red color in the medium will also increase. The intensity of the red color in the medium will also increase. So you will form a dark red color solution. So a light red color solution will turn into a darker red color solution. When ferric nitrate is added, the intensity of the red color in the medium has increased. This means that the ferric thiocyanate complex ion concentration has increased. When ferric nitrate is added, the Fe3 plus ion concentration increases, as we saw earlier. So now, according to Le Chatelier's principle, the forward reaction will be favored. And this will be favored to decrease the Fe3 plus ion concentration. Now, students, what is the meaning of forward reaction being favored? So, before we stress the equilibrium system has the forward reaction and the reverse reaction happening at the same rate, meaning the forward reaction rate and the reverse reaction rate are the same. So when certain amount of reactant molecules turn into products, simultaneously the products will turn into reactants. So whatever the reactants that are getting used up, at that instant itself gets replenished. So therefore, students, there's not going to be a change in reactant concentration or the product concentration. So at this equilibrium, if you introduce more and more reactants, or sometimes if you introduce more products, at that point you disturb the entire equilibrium. After disturbing the equilibrium, it will take some time for the new equilibrium to be established. So students, as soon as you disturb the equilibrium, before obtaining the new equilibrium, system will try to minimize the change that you brought about into the system. Whatever the stress that we introduced into the system will try to minimize that stress. So if we increase the Fe3 plus ion concentration in the system will try to decrease the Fe3 plus ion concentration while trying to obtain a new equilibrium. So this means for a short period of time, as soon as the new equilibrium is disturbed, before obtaining the new equilibrium, right? We first disturb the initial equilibrium and then a new equilibrium will be formed. So before the obtaining of the new equilibrium, there is going to be a short time period. Within this time period, one reaction will usually happen faster than the other. So when we use the word forward reaction is favored, that means forward reaction rate will be higher than the reverse reaction rate at this time period. So as soon as we disturb the equilibrium by adding more Fe3 plus, the forward reaction rate will be greater. At that point, the reverse reaction rate is slower compared to the forward reaction rate. But by the point at which we obtain the new equilibrium, again the forward and the reverse reaction rates are the same. But since the forward reaction rate was higher for a short period of time, now compared to the initial equilibrium, the product concentration has gone up because during a short period of time the forward reaction was favored. So therefore the product concentration keeps increasing. But at one point, again the forward and the reverse reactions are going to be the same. So at that point, the product concentrations will no longer change, right, from that point onwards. But before getting to that point, we saw due to the forward reaction being favored, the product concentrations start going up. But after the new equilibrium is obtained, it will no longer go up or it will no longer come down. So whatever the concentration that it had when the new equilibrium was obtained, it will maintain that concentration throughout the new equilibrium. So students, that is why we say the word favored, because during this short period of time only, the forward reaction rate or the reverse reaction rate, whatever the reaction that is favored, will be higher than the other reaction rate. It will not always, throughout the equilibrium, will be always higher. No. After obtaining the new equilibrium, again, the forward and the reverse reaction rates will be the same. So, due to this increase of Fe3 plus concentrations and the forward reaction be favored, due to this reason, the ferric and thiocyanate complex ion concentration will increase, and therefore the color of the solution change to dark red. It can be concluded, when the Fe3+ ion concentration is increased, the equilibrium position shifts to the right. So Fe3+ ion concentration increased, for reaction favored, the product concentration increases. Product is the red color complex. So therefore, we can see the medium is darker red in color. That means the equilibrium position has shifted to the right. Increasing the thiocyanate ion concentration by adding potassium thiocyanate. So we can increase the thiocyanate ion concentration by adding potassium thiocyanate. You can see when you add potassium thiocyanate, light red color solution will turn to a darker red color. Light red turn to a darker red color. So when you add thiocyanate ions, just like when Fe3+ ion concentration was increased, since thiocyanate is also one of the reactants, when you increase the thiocyanate ion concentration, to minimize this stress, according to Le-Chatelier's principle, the forward reaction will be favored. So that means in a short period of time, the forward reaction will happen faster than the reverse reaction until a new equilibrium is obtained. That means gradually the ferric thiocyanate complex ion concentration will go up, right, and will stay up after obtaining the new equilibrium. So therefore, this concentration will be higher compared to the initial equilibrium when we add thiocyanate ions into the medium. So that is why we say, upon addition of thiocyanate ions, the forward reaction is favored, equilibrium position shifts to the right, and therefore the solution will appear darker red in color. As in the case of increasing Fe3+ ion concentration, the equilibrium position shifts to the right when the thiocyanate ion concentration is increased. So this is quite similar to increasing the Fe3+ ion concentration. When thiocyanate ion concentration is also increased, the forward reaction is going to be favored, equilibrium position shifts to the right. And we can do another test. We can decrease the Fe3+ ion concentration by addition of oxalic acid, H2C2O4. So oxalic acid, when added to our equilibrium system that contains ferric ions, thiocyanate ions, and ferric thiocyanate complex ion, will be present here. So when we add this oxalic acid, the oxalate anion can form a complex with Fe3+ ions. Now this complex happens to be more stable than the ferric thiocyanate complex. So something to keep in mind. So we have the ferric thiocyanate complex here. We know the color changes as well. Now we are going to take a look at the complex that can get formed in the presence of oxalate anion. So let's first read the text here. When oxalic acid is added to the system, Fe3+ ions will form a more stable complex with the oxalate anion, which is given over here. One ferric ion will form a complex with 3 oxalate anions. Keep in mind, oxalate anion is known as a bidentate ligand. That means one ligand can form 2 coordinate bonds. So the coordination number here for ferric remains 6. So when it comes to coordination number is the number of total coordinate bonds that are formed by one metal ion. So over here there are 3 oxalate anions, and 3 oxalate anions actually form 6 coordinate bonds with one ferric ion. Each oxalate anion can form 2 coordinate bonds. Normally we only up to this point discussed anions or ligands that are capable of forming only one coordinate bond with a metal ion. Here we have a ion that can form two. We say it is a bidentate ligand, a ligand that is capable of forming two coordinate bonds with a metal ion. So therefore the coordination number here doesn't change, students, right? Coordination number of Fe3 plus here is still 6. So due to the formation of this more stable complex, we can see Fe3 plus ions, actually we can say the free Fe3 plus ions in the medium will go down. So therefore the concentration of free Fe3 plus ions, free means any Fe3 plus ions that are not present in this complex, that are freely available in the medium. So whenever Fe3 plus ions form this complex with oxalate and ions, these complexes are quite stable. So therefore this complex will not break easily to release Fe3 plus to form a complex with another ligand, right? So because of that, the free Fe3 plus ion concentration in the medium goes down. Due to the decreasing of Fe3 plus ion concentration, the reverse reaction will be favored according to Le Chatelier's principle, producing more Fe3 plus ions. Therefore, the equilibrium position will shift to the left. So students, as we see over here, when we add oxalic acid, Fe3 plus ion concentration will be brought down, right? So when Fe3 plus ion concentration is brought down, the reverse reaction will be favored. That means the equilibrium position will shift to the left. And as the reverse reaction is favored, you can see the concentration of this complex ion will go down, SCN minus concentration will go up, and gradually the Fe3 plus ion concentration will also start to go up. But it will never catch up to the initial concentration it had, right? You can't completely neutralize the change, right? So it will increase as much as possible and a new equilibrium will be obtained. And even at that equilibrium, we have to keep in mind the Kc value have to be the same as before. Kc value doesn't change when we change the concentration. So therefore, whatever the changes of concentration that take place will eventually lead to having a Kc value that is going to be the same as before in the previous equilibrium. So students, keep that in mind. One important thing, just because you change the equilibrium by adding different types of reagents or by removing different products and shifting the equilibrium position here and there, doesn't mean the Kc value will change. That is a very important thing. Kc value will only change with temperature. Over here, due to the reverse reaction being favored, the equilibrium position will shift to the left. So therefore, the dark red color in the medium will decrease and the yellowish color in the medium will increase. Then we move on to another test that can be done, addition of HgCl2, mercuric chloride, to the system, decreasing the thiocyanate ion concentration. So when mercuric chloride is added to the medium, you can see we form a complex. Mercury ions, mercuric ions and thiocyanate ions together can form a complex. Now, due to the formation of this complex, like in the formation of complex between Fe3 plus and oxalate anion, here also this complex is more stable. Therefore, the thiocyanate ions in the medium will be removed, or we can say the thiocyanate ion concentration will decrease. So let's see what we have written here. When mercuric chloride is added to the medium, a more stable complex is going to be formed. With one mercuric ion, there will be 4 thiocyanate ligands forming this complex ion, which is a more stable complex ion compared to the complex ion formed between ferric and thiocyanate ions. So therefore, it will decrease the free thiocyanate ion concentration in the medium. So now, due to some thiocyanate ions directly reacting with mercuric ion, it will form this more stable complex. Due to that, the thiocyanate ions in the medium, or ion concentration in the medium, will decrease. So according to Le Chatelet's principle, what will happen? To minimize the reduction of this thiocyanate ion concentration, the reaction that produces more and more thiocyanate will be favored. That means the reverse reaction will be favored. So students, at that point the equilibrium position also shifts to that direction, the left hand side of the equilibrium. So when that happens, we know the ferric thiocyanate complex ion concentration will also go down. Due to that, the red color in the medium will decrease, and due to the increase of Fe3 plus ions in the medium, the yellowish color in the medium will increase. As explained in the previous instances, this will lead to changing the equilibrium position to the left to minimize the decrease in thiocyanate ion concentration. So according to Le Chatelet's principle, to minimize the decrease in thiocyanate concentration, equilibrium will shift to the left. So we have another test here, adding sodium hydrogen phosphate to the medium and decreasing the Fe3 plus ion concentration. So again over here we have a way of removing the Fe3 plus ions from the medium by the addition of sodium hydrogen phosphate. So you can see when sodium hydrogen phosphate is added to the medium, Fe3 plus ions can get precipitated out as ferric phosphate solid. Ferric phosphate solid, which is a yellow-white precipitate. Right? So you will see that some Fe3 plus ions will react with this hydrogen phosphate ion that is present in the medium to produce this ferric phosphate ion. So due to this, students, due to this, the Fe3 plus ion concentration will go down. Fe3 plus ion concentration will go down, and if you have added enough and more hydrogen phosphate ions into the medium, all of the Fe3 plus ions can be removed from the medium. At that point, you will not observe an equilibrium formed between Fe3 plus and thiocyanate if all of the Fe3 plus ions are completely removed from the medium. You have to keep that in mind. When sodium hydrogen phosphate is added to the medium, the following reaction can take place. You can see it dissociates to forming sodium 1 plus ions and biphosphate or hydrogen phosphate ions. Due to the formation of ion or ferric phosphate, the free Fe3 plus ion concentration will go down. Due to this, the equilibrium position will be shifted to the left, producing more and more Fe3 plus to minimize the change. So we have another test here. We are adding sodium hydrogen phosphate to the medium and decreasing the Fe3 plus ion concentration. So students, when we add sodium hydrogen phosphate, it will dissociate in aqueous medium to form the hydrogen phosphate ions. So these ions can react with Fe3 plus ions in the medium and eventually can form ferric phosphate, FePO4, which is a solid. So it will precipitate out as a yellow-white or yellowish-white color precipitate. So what we form here is ferric phosphate, which is going to be a yellowish-white color precipitate. So due to this formation due to the formation of this particular precipitate, we can see the Fe3 plus ion concentration in the medium will decrease. This will come down. That will mean, according to the Le Chatelier's principle, to increase this Fe3 plus ion concentration, the reverse reaction will be favored. We are favoring the reverse reaction. So therefore, equilibrium position shifts to the left. So when the equilibrium position shifts to the left, that means the concentration of the ferric thiocyanate complex ion will go down. So therefore, the red color in the medium will decrease. This will also mean the thiocyanate ion concentration and ferric ion concentration will go up. Now keep in mind, although the ferric ion concentration goes up, it will never replenish the Fe3 plus ion concentration that was lost. However, it will try to recover as much as possible. So imagine the initial concentration of Fe3 plus was here, and then all of a sudden it was decreased up to this point. Carrying out the reverse reaction will try to bring it all the way up, but it never reaches the same level that was found in the initial equilibrium. It will come up and will stop before reaching the same Fe3 plus ion concentration that it had earlier in the initial equilibrium. So you have to keep that in mind. So at this point, since there are Fe3 plus aqueous ions being produced more and more, and the Fe thiocyanate ion complex ion concentration decreases, the red color in the medium decreases and the yellow color in the medium increases. So therefore, this medium will have will be either very faintly red color or while being very clearly yellowish in color. So it will be a yellow color solution mainly. So the color will shift more towards the yellowish color and the red color in the medium will decrease. So this indicates the equilibrium position shifting to the left. When sodium hydrogen phosphate is added to the medium, the following reaction can take place. First of all, the sodium hydrogen phosphate will undergo a dissociation. This is a salt, so it can form sodium and hydrogen phosphate ions. And due to the formation of ferrous phosphate, so this hydrogen phosphate ions can react with ferric in the medium and actually form ferric phosphate, not ferrous phosphate. Ferric phosphate will be formed. Here there are Fe3 plus ions reacted with PO4 3 minus ions. So it will form ferric phosphate. When ferric ions come into contact with hydrogen phosphate, it will turn into ferrous phosphate eventually, and then this will decrease the free ferric ion concentration in the medium. So now ferric ions are removed from the medium as a precipitate. Due to this, the equilibrium position will be shifted to the left, producing more and to produce more and more Fe3 plus ions to minimize the change that we have brought about. So as mentioned earlier, equilibrium position will shift to the left. Now we are going to look at the next test. Adding silver nitrate to the system and removing thiocyanate ions from the medium. So upon addition of silver nitrate, you can see silver ions coming from the silver nitrate will react with the thiocyanate ions in the medium to form silver thiocyanate, which is going to be a white color precipitate. You will be forming a white color precipitate here. So this is initially going to be formed as really fine particles of precipitate. So therefore, initially the medium will appear cloudy. After a while, you can see all of the precipitate collects at the bottom. So therefore, the white color precipitate can clearly be seen. So this is what is going to happen when we add the silver nitrate solution into our equilibrium system. So when we do this, due to silver nitrate reacting with thiocyanate in the following manner, forming silver thiocyanate solid, the silver ions will effectively remove the free thiocyanate ions in the medium. So what will happen, students, when we do that? What will happen? So the thiocyanate ion concentration will go down due to silver precipitating with it. And according to Le-Chatelier's principle, we will try to favor the reaction that will produce thiocyanate ions more and more to minimize the change that took place. So therefore, reverse reaction will be favored and the equilibrium position will shift to the left. So reverse reaction is going to be favored. That would mean the Fe3 plus ion concentration and thiocyanate ion concentration will increase while the ferric thiocyanate ion concentration will decrease. So due to the decrease of the concentration of this ion, you can see the color of the medium will, or red color of the medium will decrease, while the yellowish color of the medium will actually increase. So medium will be more and more yellowish and less red in color. So we have written it down over here. Due to the addition of silver nitrate, the thiocyanate ion concentration will decrease as they get precipitated as silver thiocyanate, a white color precipitate. Due to this, the equilibrium position will shift to the left to increase the thiocyanate ion concentration. So equilibrium position shifts to the left. And we discussed the color changes that are associated with this equilibrium position shift. So let's take a look at how the temperature affects the equilibrium position of an equilibrium system. We'll take 3 test tubes containing our ferric ion and thiocyanate ion equilibrium system, and then we will expose them to different temperatures as indicated here. So over here we have water baths that are at 3 different temperatures, one containing ice, so it will be having cooler temperatures compared to the room temperature, and then where there will be one water bath that contains room temperature water, and then we'll have another water bath that contains hot water. So the temperature will be quite above the room temperature. So we have cold temperatures, room temperature and hot temperature water baths, and we have submerged our equilibrium systems in test tubes in each of these water baths. So when the equilibrium system is subjected to a colder temperature, we can see that the color over here has changed slightly, right? So we have to observe what type of color change that happens when we subject the equilibrium system into different temperatures. And we can actually explain the changes that are taking place with the use of this equilibrium reaction and the enthalpy change for the forward reaction. So we can see the forward reaction is having a delta H value smaller than 0, or we can say delta H value is negative. That means the forward reaction is exothermic. Forward reaction is exothermic. So students, if the forward reaction is exothermic, when we submerge the equilibrium or when we subject the equilibrium to a lower temperature, then what happens? According to Le-Chatelier's principle, the reaction that produces heat will be favored when we decrease the temperature of the equilibrium system. When we decrease the temperature of the equilibrium system will try to increase the temperature by favoring the exothermic reaction that produces heat, right? So forward reaction is exothermic, as you can see over here. So at lower temperatures, the forward reaction will be favored until they obtain a new equilibrium at that temperature. Until they obtain a new equilibrium at that temperature, the forward reaction will be favored. This will result in the ferric thiocyanate complex ion concentration increasing. So therefore, the red color over here will increase, right? So the red color will increase in the medium. At room temperature, we will see that is our control. We haven't changed the temperature there, so it will remain our moderately red color as the moderately red color medium. What will happen if you add this equilibrium system to a hot environment, or what happens if we increase the temperature of this equilibrium system? So when we increase the temperature of this equilibrium system, as you know, according to Le Chatelier's principle, the system will try to decrease the temperature by carrying out the heat absorbing reaction more and more and try to reduce the temperature. So when we increase the temperature, it will absorb heat as much as possible and carry out the endothermic reaction more in hopes of bringing the temperature down. So when we increase the temperature of an equilibrium system, the endothermic reaction will be favored. So over here, if the forward reaction is exothermic, the reverse reaction would be endothermic. The reverse reaction will be endothermic. So students, at higher temperatures, the reverse reaction will be favored, meaning the ferric thiocyanate complex ion concentration will go down while increasing the thiocyanate and ferric ion concentrations. The reactant concentrations will go up, product concentration will come down. So the red color in the medium will come down and the yellowish color in the medium will go up when Fe3+ ion concentration is increased. So that is what is happening. We can take a look at it in detail here. So over here, compared to the equilibrium system in room temperature water, you can see the red color over here has increased. That means at lower temperatures, since the forward reaction is exothermic, the forward reaction was favored. This will lead to increase in the concentration of ferric thiocyanate complex ion and will decrease the thiocyanate and ferric ion concentration. So therefore, the red color in the equilibrium system will increase. Now, what happens when we introduce this same equilibrium system into a higher temperature? Then we know, since the forward reaction is exothermic, the reverse reaction is endothermic. The reverse reaction will be favored. Now, earlier on, the forward reaction was favored, and now at higher temperatures, the reverse reaction is favored, as reverse reaction is heat absorbing, meaning endothermic. So therefore, the ferric thiocyanate complex ion concentration will go down and the concentration of thiocyanate ions and ferric ions in the reactant side will go up. So this aqueous ferric ion solution is usually yellowish in color and the color over here is red, but you know the red color will come down, or the concentration of this ion comes down, so therefore the red coloration in the medium will go down while the yellowish color in the medium will come up. So these are the changes that will take place when we change the temperature of the equilibrium system. Now keep in mind, at each of these places, when we change the temperature, when a new equilibrium is obtained at that given temperature, the Kc value of the equilibrium is changed, right? So at lower temperature, the Kc value is different to the equilibrium at room temperature, and the Kc value will be different to the equilibrium at higher temperatures compared to the other two equilibriums as well. So Kc value will change when you change the temperature of the equilibrium, but Kc value will never change when you change the concentration of the equilibrium. So you will change the equilibrium position when you change the concentration of reactants and products, but will never change the Kc value. It will never change the Kc value. If you maintain the same temperature while changing concentration, the Kc value will not change. Kc value will only be affected by a temperature change. So we have a summary of the test that we did here today. So we have, if you heat the system, we saw the reverse reaction was favored. Why? Because the forward reaction was exothermic. When you heat the system will try to decrease the temperature by absorbing more and more heat. That means by favoring the endothermic reaction. Reverse reaction was endothermic, so therefore reverse reaction was favored. Equilibrium position got shifted to the left. When you cool it, since the forward reaction was endothermic, forward reaction was favored, so therefore equilibrium position got shifted to the right. Addition of ferric nitrate. So ferric nitrate increased the ferric ion concentration. To decrease the ferric ion concentration according to Le-Chatelier's principle, the forward reaction was favored. So therefore equilibrium position also gets shifted in the same direction. When the forward reaction is favored, equilibrium position also shifts to the right. When sodium hydroxide was added, we formed ferric hydroxide and Fe3 plus ions were precipitated as ferric hydroxide. So therefore Fe3 plus ion concentration went down. To increase the Fe3 plus ions according to Le-Chatelier's principle, the reverse reaction was favored. So equilibrium position gets shifted in the same direction to the left. So addition of sodium hydroxide shifted it to the left. Addition of potassium thiocyanate solid will increase the thiocyanate ion concentration. So therefore the forward reaction will be favored to decrease the thiocyanate ion concentration according to Le-Chatelier's principle. So equilibrium position will shift to the right. If you add oxalic acid, we saw oxalic acid will combine or will form a complex with Fe3 plus ions, which is going to be more stable than the complex formed between Fe3 plus and thiocyanate ions. So therefore Fe3 plus will be removed from the medium as a complex between Fe3 plus and oxalate ions are formed. So free Fe3 plus ion concentrations will go down. To mitigate this, the reverse reaction will be favored. So when the reverse reaction is favored, the equilibrium position will shift to the left. When it comes to mercuric chloride, we can see the mercuric ions form a complex with the thiocyanate ions, which happens to be more stable than the complex between Fe3 plus and thiocyanate. So therefore thiocyanate ion concentration in the medium goes down. So free thiocyanate ion concentration is less now. So to make sure that we somehow increase this thiocyanate ion concentration, the reverse reaction will be favored in the Fe3 plus thiocyanate equilibrium. So therefore equilibrium position will shift to the left. When sodium hydrogen phosphate is added, the hydrogen phosphate ions that are now in the medium will react with ferric ions to eventually form ferric phosphate, which is a yellowish white precipitate. So therefore ferric ion concentration goes down. To neutralize this change, or to minimize this change, not neutralize this change, to minimize this change, the equilibrium will shift to the left by favoring the reverse reaction more. And eventually, students, we also saw when silver nitrate is added. Silver nitrate, silver ions and thiocyanate ions will form a white color precipitate, silver thiocyanate. So therefore thiocyanate ion concentration goes down. To increase the thiocyanate ion concentration, the reverse reaction was favored. In doing so, the equilibrium position got shifted to the left. So these are the changes that take place when we add these reagents to the equilibrium system. And afterwards, we also looked at how the temperature changes the equilibrium position as well. So students, with this, we can conclude the theory parts revolving around experiment number 33. So I hope you have gotten a good grasp of the theory parts that are associated with this equilibrium. So with all of these theory in mind, we can now move on to the lab and actually conduct this experiment and observe the aforesaid observations. So let's move on to the lab. GCE Advanced Level Chemistry Practical Series, experiment number 33. Experimental study of the characteristics of a dynamic equilibrium with the use of ferric ions and thiocyanate ion equilibrium system. The aim of this experiment is to develop a better understanding of a dynamic chemical equilibrium. Furthermore, we are going to observe how
an equilibrium behaves when it is applied with certain stresses. Without further ado, let's move on to identifying the reagents we will be using for this practical. Let's take a look at the reagents we will be using for this practical. We have over here our ferric nitrate solution, which we have prepared by dissolving ferric chloride in nitric acid. When it comes to ferric salts, salts containing Fe3+ ions, when you dissolve them in water, you normally observe a yellow-brown color solution. This is due to Fe3+ ions deprotonating the water ligands that are attracted to it and forming ferric hydroxo complexes. These are usually yellow-brown in color. So if you add an acid to this deprotonation would be reversed, and therefore you will form water ligands, or surrounding Fe3+, you will have water ligands, and this aqua complexes or hexa-aqua Fe3+ complexes will be brown in color. So this is why you observe the Fe3+ ion solution that we have here to be brown in color. And then we have our potassium thiocyanate, and we have our sodium hydroxide. We have another beaker for the control solution, and we have 4 test tubes labeled 1 to 4, so that we can very clearly identify which reagent has been added to which test tube. We will be using droppers to add reagents as well. Now, let's move on to our practical. First, let's take the beaker that is labeled control. Now, let's move on to adding ferric ion solution to our potassium thiocyanate solution. So let's first take our ferric nitrate solution that we have here, and let's add it to our beaker here that is labeled control. And then to it, we'll add a little bit of potassium thiocyanate. Now, potassium thiocyanate, when reacted with Fe3+ ions, will form a blood red color solution. Let's observe the formation of this blood red color solution. We can see here, when Fe3+ ions comes into contact with thiocyanate ions, it forms a blood red color solution. Now, let's add water until we observe an orange color in this beaker. It is still red in color. We need an orange color. As we add water, we are diluting the solution. As this solution is quite concentrated, we can take another beaker and dilute it a little further. As you can see, now we are reaching an orange color. Now we have diluted our blood red color solution to an orange color solution. When we are starting off, the Fe3+ ions were brown in color, but as you know, as time passes by, when more and more deprotonations happen, Fe3+ ion solution eventually end up looking yellow in color or yellow brown in color. As you can see, even our ferric nitrate solution is no longer that brown. It is changing color as more and more deprotonations take place in the aqueous medium. So the initial solution when Fe3 plus ions are present in the medium was yellow in color. And then when you are adding thiocyanate ions, what happens is due to the reaction between Fe3 plus and thiocyanate, we produce iron thiocyanate complex, thiocyanate iron 3 ion. So this complex is going to be blood red in color. The mix between this blood red color complex and the yellow color Fe3 plus complex is orange. So, or this particular beaker with the controlled solution in it, you can see the color of the solution is orange. This is due to the presence of a yellow color complex as well as a blood red color complex together. Both of those colors together appear orange. Now what we are going to do is we are going to remove 4 portions of this solution into these 4 test tubes. Like so, we'll take one test tube and pour a small amount of the solution into each of these test tubes. Now we have added our control solution into 4 separate test tubes, and in these test tubes we will not add anything to the solution in the first test tube or the test tube labeled 1. So it is easier to compare the colors when they are all in test tubes. We will not add anything to the test tube 1. So test tube 1 will act as our control solution in this test tube rack. To the second test tube, we will add a little bit of sodium hydroxide. As you can see, upon addition of sodium hydroxide to this test tube 2, we can see the color of the initial solution changed slightly to a lighter color, more towards yellow. The control is here. You can see if you're taking a look at the control test tube that we have here. The control test tube has an orange color, and after adding sodium hydroxide, the color of the solution in test tube 2 appears to be a little yellow in color. Make note of these observations, and then we move on to test tube 3. To test tube 3, we will be adding a little bit of ferric nitrate again. Observe what happens to the color of this test tube, of the solution in this test tube. As you can see, when you keep adding ferric nitrate to this control solution, you can see the color changed from a lighter orange color to a darker orange color. If you compare it against the control solution we have here, you can see very clearly it has gone from this orange color over here more towards a red color or a darker orange color. Now lastly, Let's move on to our test tube 4. To that, we will add potassium thiocyanate. Let's take a few drops of potassium thiocyanate and add here. As you can see, when even a single drop of potassium thiocyanate is added, you can see the color changing more towards a darker orange color. The initial solution was a lighter orange color, but when it comes to the second test tube, or the fourth test tube rather, that we have here, is a darker orange color. Let's add another drop to see if the color changes a little bit more. As you can see, the more potassium thiocyanate we add, the closer it will get to a blood red color or a red color. It is moving away from the orange color that we have here, and it comes closer to a red color. Now students, let's take a look at what has happened here. Let's take our ferric nitrate solution here. The color of the ferric nitrate is slightly yellow in color, or yellow brown in color. And when you added potassium thiocyanate to it, we turned this yellow brown solution into a blood red color. So you can see these are the two colors that you observe in the two extremes of this equilibrium. Before adding potassium thiocyanate, the solution looks more yellowish, and after sodium cyanate has been added, the solution appears more blood red in color. What we have obtained here is a small volume of this blood red color solution, and we have diluted it until we obtain an orange color, a color that is in between these two extremes of the equilibrium. And then to this orange color solution, we added a little bit of sodium hydroxide. And when adding sodium hydroxide, you can see the solution turns more towards a yellow color, and even a small precipitate of iron 3 hydroxide or ferric hydroxide has been formed here. This is the ferric hydroxide precipitate you see at the bottom, and the solution is more towards a yellow color. As Fe3+ ion concentration goes down, equilibrium position shifts more towards the left hand side, producing a more yellowish color in the solution. If the equilibrium position go more towards the right hand side, where iron thiocyanate complex ion is formed, the solution would look blood red or closer to blood red color, because the two extremes of this equilibrium is Fe3+ aqueous ions, and on the right hand end we have iron thiocyanate complex, iron 3 or thiocyanate iron 3 complex. So if you take the control that we have and add a little bit of ferric ions to it, then in the equilibrium the ferric ion concentration will go up. This stress that is caused to the equilibrium will be remedied by making the reaction go more towards the right hand side, producing more and more ferric thiocyanate complex. So you can see this is evident by the darker color that is present in this test tube. The control is light orange, but test tube 3 is a darker orange, more towards a red color. This is due to the formation of ferric thiocyanate complex. And in test tube 3, we increased yet another reactant concentration. The concentration that we increased in this particular experiment was thiocyanate ion concentration. So thiocyanate ion was one of the reactants we had. So when we increased the reactant concentration, we started producing more and more products to relieve the stress that is added on to the system by increasing the thiocyanate concentration. So therefore, the thiocyanate concentration goes up. To counter that, the equilibrium position will shift further to the right hand side, producing ferric thiocyanate complex, which is blood red in color. So there's more of a production of ferric thiocyanate complex, which is going to be blood red in color. So the color over here is darker compared to our control, as you can see. This indicates the equilibrium has shifted more towards the product side. When we were adding sodium hydroxide, equilibrium has shifted more towards the reactant side, because by adding sodium hydroxide, we have decreased the concentration of Fe3+ ions in the medium. This is a summary of this experiment. Now, let's move on to our questions and important theory parts revolving around this experiment.
Students, we have now taken a look at how we conduct the experiment, and we are going to now move on to doing some questions revolving around the experiment number 33. So let's take a look at the first question. First question is asking us about Le Chatelier's principle. The first one is, state the Le Chatelier's principle and then explain how you can use ferric and thiocyanate ion equilibrium system to demonstrate the effect of concentration on the equilibrium. Now, for the first question, Le Chatelier's principle. As you know, Le Chatelier's principle states that when you take a system that is at equilibrium, and when you introduce some sort of stress to this equilibrium system, the equilibrium system will try to relieve the stress that we apply on it. Now, a stress can be a change in the concentration of reactants or products, a change in pressure, or change in temperature. So we have learned, when we increase the reactant concentrations, the forward reaction will be favored and a new equilibrium position will be established, and due to that, the product concentration will slightly go up. So basically, students, when we increase the reactant concentration, according to Le Chatelier's principle, we will be carrying out we will see that the equilibrium is trying to relieve this stress that we have applied on it by carrying out the forward reaction more. So that when we carry out the forward reaction more, the additionally added reactant concentrations are going to be brought down. So we additionally externally added reactant concentrations to an equilibrium system, and at that point, to relieve this stress, the forward reaction will be favored to decrease the reactant concentration or decrease the effect of what we have done. When we increase the pressure, system will try to decrease the pressure. When we increase the temperature, system will try to decrease the temperature. So students, this is what Le Chatelier's principle states. And then we also have explained how you can use ferric and thiocyanate equilibrium system to demonstrate the effect of concentration on equilibrium. How we can demonstrate the effect of concentration on equilibrium. So we will take a look at how this is done. First, let's answer the first part of this question. State the Le Chatelier's principle. Now, Le Chatelier's principle states when system at equilibrium is subjected to a stress can be change, we can write changing concentration, pressure, or temperature. The system will react so as to relieve the stress. So this is something you have to keep in mind. When we are applying a stress to a system at equilibrium, the equilibrium system will try to relieve that stress. And that is what Le Chatelier's principle states. Explain how you can use the ferric ion and thiocyanate ion equilibrium system to demonstrate the effect of concentration on the equilibrium. Now, students, we have ferric ions solution, let's say AQ here, and we can introduce thiocyanate ions to this ferric ion solution. At that point, you will see an equilibrium established. We will see a reaction happening first. After a while, an equilibrium will be established. So here, we are going to be producing Fe3+SCN complex So when this complex is formed, it is going to be a very clear observation because Fe3 plus aqueous ion solutions are going to appear yellow brown in color. Thiocyanate ion solutions are colorless. There is no color observed when it comes to the thiocyanate ion solution. But when a thiocyanate ion solution drop O2 is added to a Fe3 plus ion solution, you will see the formation of a really red color solution. So here, this is going to be a red color solution. So students, now this red color is very prominent. It is also often referred to as a blood red color. So thiocyanate ions, when they form complexes with ferric ions, due to formation of this complex, you are going to observe a red color in the solution. And keep in mind, since this is an equilibrium, we also have these ions still present in the medium. However, this ion is colorless and this ion is yellow-brown in color. But this yellow-brown color of the Fe3 plus ions in the medium are going to be masked due to the formation of this color. So this red color is very prominent. So therefore, the Fe3 plus ions in the medium, their color will not be properly observed. So now we can first mention, when you are talking about how we can show that this equilibrium is affected by changes of concentration, you can first say we take a small volume of Fe3 plus ion solutions and then we are going to add a few drops of our thiocyanate ion solution. And then
if the red color is too prominent, we are going to dilute it a little bit until we observe a slightly lighter red color, because we need to observe when we are changing the concentration of these different reactants and products, we need to see if the color intensity of red is increasing or whether it is decreasing. So based on that, we can figure out whether the reaction has proceeded in the forward direction or the reverse direction. So because of that, students, we are not going to be working with a really dark red color solution, because in that case, imagine due to a change that we do, equilibrium position shifts to the right, then what happens? This concentration further increases. So students, if the solution is already very dark red, increase of this concentration will contribute to the red color being a little bit more darker. But if it is already dark red, you will not be able to properly distinguish the fact that the color has gotten more intense, because it's already quite dark in appearance. But imagine when the color of the solution is light red, if this concentration increases, then we can very clearly see the light red color solution becoming darker red in color. The red color intensity has gone up. So you will be able to very clearly observe that change if you take an equilibrium system that has a lighter red color to begin with. So students, you are going to see here the observations very clearly when you do that. So we are going to be doing just that. So we can now state how we do this experiment. We can first take to a small volume of Fe3 plus aqueous solution, few drops of SCN minus aqueous solution is added. If the color intensity of the solution is too high, water will be added to obtain a solution with a moderate color intensity. Then the following solutions can be added to change the equilibrium concentrations. First test that we can do is addition of
oxalic acid. Now students, when oxalic acid is added, as you know, oxalic acid dissociates to form H plus and oxalate ions. And these oxalate ions can form complexes with Fe3 plus ions in the medium. Oxalate ions can form complexes with Fe3 plus ions in the medium. So they form this complex that I write over here. And these complexes are quite stable. So therefore students, they won't again break up releasing Fe3 plus. So what happens over here is the Fe that forms complexes with oxalate ions will be removed from the equilibrium system because the formed complex is not releasing Fe3 plus that easily. So therefore students, Fe3 plus that goes into forming this complex is effectively removed from the equilibrium system we saw earlier. So because of that, now we have an equilibrium system over here. That equilibrium system is now going to have lowered Fe3 plus concentration because some of the Fe3 plus is now getting used to form Fe3 plus oxalate complex. Now oxalate anion is a bidentate ligand. It's a bidentate ligand. So that's why we see over here there are only 3 oxalate anions forming coordinate bonds with Fe3 plus. Keep in mind students, although there are only 3 oxalate ions, there are 6 coordinate bonds formed here, and each oxalate anion is capable of forming 2 dative covalent bonds with Fe3 plus. So we say this is a bidentate ligand because of that. That means with single ligand 2 bonds can be formed. Now EDTA, if you remember, EDTA is a compound that can form 6 dative covalent bonds with a metal cation. So we say it's a hexadentate ligand, or we sometimes also refer to it as a multidentate ligand. So these are things that you can revise while doing a question like this. So students, if you briefly write the equation for the ferric ion and thiocyanate ion equilibrium once more. Over here, due to the Fe3 plus ions getting used up in the formation of ferric oxalate complex, the Fe3 plus ions available in the medium as free Fe3 plus ions. Free means there are available Fe3 plus ions that are freely available to form complexes as anything is going to go down. That means in the aqueous medium, these free Fe3 plus ions that can form a complex with thiocyanate ions decrease. So this concentration goes down. We can write the Fe3 plus ion concentration over here decreases, and this is a stress that is introduced into the equilibrium system. So we have removed Fe3 plus by reacting it with oxalate ion. Now if you take a look at the equilibrium, according to Le Chatelier's principle, equilibrium system will try to relieve the stress that we have introduced. So the reverse reaction is going to be favored for a while until a new equilibrium is obtained. So due to the favoring of the reverse reaction, the Fe thiocyanate complex concentration will go down in attempts to increase this Fe3 plus concentrations. Now, due to the favoring of the reverse reaction, you will see thiocyanate concentration and Fe3 plus concentration will slightly increase. That means Fe thiocyanate complex concentration will decrease. So, if we are going over the steps once more, first thing that takes place, students, is the lowering of Fe3 plus due to the addition of oxalate ions. Due to formation of this complex, Fe3 plus ion concentration will go down. That is the stress we have introduced to the system. Now, system will try to relieve that stress by favoring the reverse reaction more and more and producing this Fe3 plus more and more. We decrease the Fe3 plus, system will try to increase the Fe3 plus. And in attempts to do that, when they favor the reverse reaction, the Fe thiocyanate complex concentration goes down, while these concentration slightly go up. So, due to this, we say the Fe thiocyanate complex concentration goes down. So, therefore, the red color that you see over here, due to this complex being there in the medium, the red color intensity of the solution will decrease. You will very clearly observe the red color intensity of the solution will decrease. You can write over here the intensity of the red color in the solution will decrease This indicates that the equilibrium position has shifted to the left due to favoring the reverse reaction. So we can very clearly see that the equilibrium position was shifted to the left due to favoring the reverse reaction. So therefore, Fe3 plus and thiocyanate ion concentrations will slightly increase in attempts to overcome the stress that we have introduced, and due to favoring the reverse reaction, ferric thiocyanate ion concentration will decrease, and because of that, the color intensity of the solution will decrease. So it will no longer be a moderately red color, it will slightly be a lighter red in color. Apart from this, we can also add another stress to the system, right? Addition of, we can add HgSO4, mercury sulfate. So again, mercury sulfate also can dissociate in water in the following manner. HgSO4 can produce Hg2 plus aqueous ions along with sulfate aqueous ions.
And these produced sulfate or mercury ions, actually not the sulfate ions, the mercury ions over here can react with thiocyanate ions. In fact, actually 4 thiocyanate ions to produce a stable complex HgSCN 4 2 minus. This is a complex that is quite stable. So again, these thiocyanate ions that go into forming this complex will not be released back into the medium easily. So therefore, students, these thiocyanate ions are effectively removed from the equilibrium system that we saw earlier. So if you rewrite that equilibrium system over here, we see here we have Fe3 plus reacting with thiocyanate ions, forming FeSCN 2 minus aqueous. So in this scenario, what we do is introducing a stress by addition of mercury ions. Mercury ions will react with the thiocyanate ions and will remove thiocyanate ions from the medium by forming that complex. So therefore, thiocyanate ion concentration will go down. So this is the stress that we introduce. So due to this stress, according to the Le-Chatelier's principle, you know, the system will try to relieve the stress. But over here, due to lowering of the stress, the reverse reaction will be favored. Now, first of all, whenever we do any change to the equilibrium, we say the equilibrium is disturbed. We say the equilibrium is disturbed. That means now we are on our way to establishing a new equilibrium. So as soon as this stress is introduced, the current equilibrium is disturbed and the reverse reaction is going to be favored in the initial parts of establishing a new equilibrium. So the reverse reaction is favored, trying to relieve this stress that we have added. So when the reverse reaction is favored, we are trying to increase the thiocyanate ion concentration, right? So when the reverse reaction is favored for a short period of time until a new equilibrium is obtained, the ferric thiocyanate complex concentration goes down because the reverse reaction is favored, ferric thiocyanate ion concentration decreases. So when the reverse reaction is going to be favored, at that point this concentration will go down as the reverse reaction is the one that is favored. So this is only in the beginning, students. Now after a while, when the new equilibrium is established, you will see the forward and the reverse reaction rates are going to be the same. But at that point, this would have decreased sufficiently for us to observe a color change, right? So when the new equilibrium is obtained, the equilibrium position would have shifted to the left. Okay, right, students. So apart from that, we can do a few additional changes. Now we actually decrease this thiocyanate ion concentration. We decrease the ferric ion concentration as well. Now to decrease the ferric ion concentration, you can also add Fe solid or iron solid, because as you know, now I'm going to go over a few ways in which you can change the concentration of these reactants. So in this case, we can just add Fe solid into the medium. At that point, it will react with Fe3 plus and will form Fe2 plus. Right, students? So what happens is you will see that ferrous or iron actually gets oxidized to form ferrous, and ferric will get reduced to form ferrous. So you have iron that oxidizes, right, to form ferrous. So there are 2 electrons that are released, and those 2 electrons are going to be taken by 2 ferric ions to form 2 ferrous ions, and this ion that we introduced will be turning into 1 ferrous ion. So this actually removes some of the Fe3 plus from the medium, again lowering the Fe3 plus ion concentration and favoring the reverse reaction. Now apart from that, we can also talk about increasing these reactant concentrations. That's another option. Now those options are quite easy. So I hope at this point you have developed an idea about what you should write when this type of question is asked. So just to repeat and show how we can actually write a small explanation when it comes to increasing a reactant concentration, we'll take a look at the third observation as well. Before we go ahead, we will write a small explanation here. We can write, due to the lowering of SCN minus concentration, the reverse reaction is favored, and the equilibrium position will shift to the left. This causes the Fe3+SCN concentration to decrease, thereby lowering the red color intensity in the medium. So this indicates that the equilibrium has shifted to the left. Equilibrium position has shifted to the left when we change the reactant concentration. And one additional step that you can do is addition of FeCl3, ferric chloride into the medium. So we know FeCl3 when dissolved in medium, it will turn into Fe3 plus aqueous and Cl minus aqueous. So now students, you know we have increased the ferric ion concentration. So over here we will see when you do this, Fe3 plus aqueous, we have the SCN ions as well here. Now this equilibrium will be affected due to this. What will happen? what will happen? You will be able to answer it at this point. You will observe when Fe3 plus ion concentration is increased, when this ion concentration is increased by addition of ferric chloride, we have introduced more and more Fe3 plus. Now this ion concentration increases quite a bit. So then what will happen according to Le-Chatelet's principle? The forward reaction will be favored. So you can see the forward reaction is favored momentarily until a new equilibrium is obtained. So due to that, the ferric thiocyanate ion complex concentration will increase. And because of this, students, the red color intensity over here will increase. The red color intensity over here will increase. So you can finally write, when Fe3 plus ion concentration is increased, the red color intensity will also increase. This indicates that Fe3+SCN concentration has increased. This indicates that due to the increase of Fe3 plus ion concentration, equilibrium position has shifted to the right. So this very clearly indicates that the concentration of reactants and products are important, right? So when you change the concentration, we can see the equilibrium position shifts to relieve the stress that we have introduced. If you take a equilibrium system, if you increase the concentration of one reactant, that is a stress we have introduced, and to decrease the change that we have introduced, the equilibrium will favor one forward or either the reverse reaction for a while when establishing a new equilibrium. And this is what was stated in the Le-Chatelet's principle, mentioning that when we introduce an external stress into an equilibrium system, then the equilibrium system will try to relieve the stress. So in this case, when we have introduced more and more Fe3 plus ions, which is a reactant, to reduce this reactant concentration, they have favored the forward reaction, producing more and more products. So the reactant concentration goes down and product concentration slightly goes up. So students, this is the answer to the question that was asked. So we can talk about increasing, decreasing Fe3 plus ion concentration, increasing, decreasing this SCN ion concentration, and observing the changes that take place. If the forward reaction is favored due to increase of a reactant, you will see the red color of the solution is now increasing. The red color intensity is increasing. If you remove one of these reactants, we saw due to the lowering of the reactant concentration, the reverse reaction was favored, and at that point the complex ion concentration went down. So because of that, the red color intensity in the medium also went down. So that was the answer to this question. So now we can move on to the next question. Explain how you would demonstrate through qualitative means that the reaction between HBr and sulfuric is reversible. So students, when HBr and sulfuric acid, when HBr and sulfuric acid is reacted, we have a reversible reaction taking place here, producing Br2, bromine gas, sulfur dioxide, and water. Right, so these are aqueous, and we will be forming these gases: bromine gas, sulfur dioxide gas, and water. Now we have to show that this reaction is reversible. So students, you can straight take HBr and react with sulfuric acid, and you will see the formation of a brown color gas. Apart from that, a pungent smelling gas that can bleach the color of wet flower petals is also formed. So bromine gas is very easy to identify. It will have its own color, red color, and the sulfur dioxide gas produced, that is produced over here, has a very pungent, harsh smell. And apart from that, if you take a wet flower petal and if you expose it to the sulfur dioxide gas, when the sulfur dioxide gas comes into contact with this, you will see the color of the flower petal. You have to take a colored flower petal, not a white one. So if you take a pink color flower petal, you will see the flower petals color will be disappearing in the presence of sulfur dioxide, or the flower petal has to be made wet first, and then when you expose it to sulfur dioxide, you will see the color of the flower petal will disappear. So the color is bleached. So students, this is how it's done. So in the lab, if you want to do this, we can take KBr. If you don't have HBr, we can take KBr. We can take KBr and react it with concentrated, right? Concentrated sulfuric acid. Now at that point, we are going to first form HBr and potassium bisulfate or potassium hydrogen sulfate, and this HBr produced will further react with the sulfuric in the medium, and you will observe the formation of Br2 along with sulfur dioxide gas and water. Br2 along with sulfur dioxide gas and water. So students, this equation has to be balanced. So there are two bromines here, and we are going to be obtaining two water molecules here as well. So you can see 2Br. Apart from that, we have 4H over here. So you can see in water also there are 4 hydrogens. So hydrogen number is balanced. If you take a look at the oxygen number, there are 4 oxygens over here, and 2 plus 2, 4 oxygens, and sulfur number is already balanced. So now we will be moving on to showing. Now this of course is, like I mentioned over here, when this reaction takes place, the observation is very clear. You will see the formation of a brown color gas, and even the medium might turn a little brown due to bromine gas dissolving in water. Due to the bromine gas dissolving in water, you will see the medium will also turn brown or red-brown color, but you will see the emission of a brown color gas. Apart from that, you will see sulfur dioxide being produced. Actually, that is not a visible observation. You will feel the pungent smell, and apart from the pungent smell, you will also be able to confirm the presence of sulfur dioxide by bringing a wet colored flower petal to the sulfur dioxide gas that is evolved. So when sulfur dioxide gas and this wet flower petal comes into contact with one another, the color of the flower petal will disappear. So students, this is the equation that is written for this reaction. Over here also we'll have to balance the equation above. Now, how can we show that this reaction is reversible? How can we show that this reaction is reversible? We can take a aqueous bromine solution, Br2AQ. Now this is going to be red brown in color, or based on the concentration of bromine, it might have a light brown color. And then we are going to send sulfur dioxide gas through it. We'll be sending sulfur dioxide gas through it, right? So when sulfur dioxide gas is passed through it, you will observe this brown color in the solution. Brown color in the solution will disappear. The brown color in the solution will disappear, and you will observe a colorless solution being formed. So this is the observation. So this indicates that this reaction is reversible. Now, what is taking place here? We have bromine, Br2 aqueous. This is the brown color solution. And with it, we are reacting sulfur dioxide, right? So sulfur dioxide gas is introduced, but when sulfur dioxide gas reacts with this bromine in the presence of water, this is happening in aqueous medium, so therefore we have water here in the presence of water. You will see that this turns into HBr, H2SO4. So this is why we say that this reaction is reversible, because we can do this reaction in either direction. So you will be forming two HBRs, and two water molecules will be used up in this reaction. So here you don't have any colored compounds. All of these are colorless. And if you want to take it a step further to very clearly identify that what we have formed is bromide ions and sulfate ions, we can do identification tests for sulfate and for bromide ions, right? So for sulfate, we can say to the resultant solution, we are going to add barium chloride, BaCl2. So at that point, students, we can see the barium ions in the medium. We know this dissociates to produce barium and chloride ions. So barium 2 plus ions in the medium will react with sulfate ions in the medium to form barium sulfate solid, which is a precipitate, white color precipitate. So the formation of this white color precipitate indicates that this reverse reaction has happened. Earlier in the medium, we had bromine and sulfur dioxide was bubbled through it. There was no other ions that could have precipitated with barium. But after the reaction has taken place, we know we are producing sulfate ions and bromide ions. And sulfate ions can precipitate out with barium. So if this precipitate is formed when barium chloride is added to that resultant solution, that is an indication that the reverse reaction that we expected has happened. In this case, that means this particular reaction, as we have written it, has happened. To observe the presence of bromide ions, we can add silver nitrate. Silver nitrate can be added. Silver nitrate solution can be added. So at that point, the silver ions that are coming into the medium, can react with the bromide ions that were formed in the earlier equation or earlier reaction, and will form silver bromide. This is again a off-white or pale yellow precipitate. And we can say, if you want to further confirm the presence of silver bromide, we can add concentrated ammonia solution. The precipitate dissolves. The precipitate will dissolve. So it will not dissolve in aqueous ammonia or dilute ammonia, but in concentrated ammonia, it will dissolve. So students, this is what takes place, or this is how we can actually show that the above equilibrium that is given here is reversible. We can initially show that HBr and sulfuric acid will react to form bromine and sulfur dioxide, and we can observe the presence of bromine through its color and sulfur dioxide through an experiment. And if you do the reverse reaction, which is basically taking a bromine aqueous solution and bubbling a sulfur dioxide gas through it, we saw the bromine's color in the aqueous medium will disappear. That itself is an indication that bromine reacts with sulfur dioxide. But to confirm that they have reacted to form these two as products, we can do the further identification test that we discussed earlier. We can add barium chloride to identify the presence of sulfate ions. So that means sulfur dioxide has turned into sulfate. And to identify bromide ions, we can take silver nitrate and add that into the resultant solution. So when bromide ions are present, you will see the resultant solution is going to produce a yellow color, pale yellow color precipitate. And this precipitate will dissolve in concentrated ammonia, not in dilute ammonia. With that, we have now effectively indicated how this particular equilibrium reaction is a reversible reaction. We have shown that this equilibrium that we have written is a reversible reaction. Now with that, we can move on to the next question. So let's take a look at the third question. So first, they're asking us to consider the equilibrium given below. We have A gas reacting with B gas, producing gas C and gas D. and the simple letters over here represent the stoichiometric coefficient of each of the reactants and products. And the question over here is, they are asking us to show the relationship between Kp and Kc for the above equilibrium. And then in the second question, it is mentioned that 3 moles of ethanoic acid and 13 moles of methanol was allowed to reach an equilibrium at a specific temperature in the presence of sulfuric acid. Now, sulfuric acid is a catalyst here, because we know when ethanoic acid and methanol or carboxylic acid react with an alcohol, the reaction that is taking place is an esterification reaction, and this requires a catalyst, and the catalyst is going to be our concentrated sulfuric acid. Through this reaction, 2.8 moles of ester was produced. Ester is the product. Calculate the Kc value. So in other words, students, they have given us the initial number of moles of the reactants. They haven't mentioned how many moles of each of these reactants actually reacted. However, they have mentioned the equilibrium number of moles of the ester that is produced. So based on that, you have to find out the Kc value. So let's first complete the first question here. So let's move on to the first part of question number 3. Consider the equilibrium below and show the relationship between Kp and Kc. So first, let's write these expressions. So Kp uses partial pressures, right? Kp uses partial pressures. So partial pressures of the products that are present here, and they are going to be raised to their stoichiometric coefficients. So we can say partial pressure of C gas, and it should be raised to its stoichiometric coefficient, so it's simple C over here, multiplied by partial pressure of D gas raised to its stoichiometric coefficient over here, D, divided by partial pressure of A gas to its stoichiometric coefficient A, multiplied by partial pressure of B gas raised to its stoichiometric coefficient. So this is a Kp expression. And if you write Kc expression, it is going to be the reactant concentration or product concentration divided by reactant concentration. So product concentrations are going to be C gas concentration. Again, here also these values should be raised to their stoichiometric coefficients. And then we have D gas to the power simple D divided by A gas to the power simple A and B gas to the power simple B. So the square brackets indicate that we are considering their concentrations, not the partial pressure. Here we are considering each of these gases' concentration. Now, when we are trying to identify a connection between the two, it is important to remember something. That is, if we are conducting this experiment, or if we have this equilibrium system in a container like this, and if it has a volume V, and the pressure inside the container is P, and we have a temperature of the system T, right? And then this equilibrium is going to be having different number of moles. If you take a look at these details, and for each of these gases, considering that they are behaving ideally, we can write an expression like this: PV equals nRT. For a specific reactant, let's say reactant A, we can write PV equals nRT equation for that. PV equals nRT. So at that point, if you are talking about its partial pressure, now we are talking about, let's say, only the gas A. Let's say we are only talking about gas A, right? So at that point, P over here is going to be partial pressure of gas A. So we'll say PA, right? Volume is going to be V for everything. So we'll say just V. And here NA, number of moles of A. And temperature and R is a constant because temperature is not changed while this experiment is carried out. And volume is also not changing. So for partial pressure of A, we can write an expression that is NA divided by V multiplied by RT. Now when you do that, students, we can see partial pressure of A is equal to these other terms that we have mentioned over here. And if you observe closely, NA divided by the volume of the entire container is going to be the concentration of gas A. So that means we can write partial pressure of A is equal to concentration of gas A multiplied by RT. So just like this, students, we can write equations for other gases' partial pressures as well. So PA, or partial pressure of A, is equal to concentration of A multiplied by RT. And when it comes to partial pressure of B is going to be equal to concentration of B multiplied by RT. So P equals CRT. So now, students, based on that, we can rewrite this expression number 1 over here, right? So for each of these partial pressures, we can write an expression. So instead of writing P, our partial pressure of C, we can directly write concentration of C, right? Concentration of C multiplied by RT. So this is the partial pressure of P over here. We have written PC. So partial pressure of P can be written like this. Keep in mind, this has to be raised to the power C. And it is multiplied by partial pressure of D, then RT. So partial pressure of D can be written like this: concentration of D multiplied by RT to the power D. So what we are basically doing is, instead of writing the partial pressure, we are using this expression. Partial pressure of A is equal to concentration of A multiplied by CRT. So concentration of A, you normally don't write it like this. We usually write concentration of A, right? For example, if we write partial pressure of A is equal to concentration of A, we write concentration of A this way, and then RT. So this expression is what we can write for the partial pressure of A. So similarly, we have now written partial pressure of D and C over here, and keep in mind they are raised to their stoichiometric coefficients here when writing Kp value. So here we are still completing this equation. So we have partial pressure of A and partial pressure of B over here. So partial pressure of A is equal to concentration of A multiplied by RT, and this entire thing is raised to the power A. And then we have partial pressure of B multiplied by RT, and this entire expression is raised to the power B. And then, students, if you observe this, we can actually take these concentrations out, as RT is a constant for every expression here, or it is seen in every term here. So we can take RT out and we can take the concentrations to a single side. So at that point, you will see concentration of C. So when you're removing the concentration, you have to remove it along with the power here. So concentration of C to the power C multiplied by concentration of Now in each of these cases, don't forget the state here. There should be gas in each of these cases. So C gas concentration, D gas concentration divided by, now there are RT values, I'll get to that in a second. Here we have A gas concentration and B gas concentration. Keep in mind, whenever you take B out, you have to take this power as well. And apart from that, we have this RT term in each of these numerator and the denominator. You have RT, and they are coming along with these powers. So when the bases are the same and if they are multiplying, we know powers are adding up. So over here we have power C plus D. Over here we have RT added with power A plus B. So in this situation, we can very clearly see these four terms together make up this expression, doesn't it? So Kc expression is seen here as well. So this whole thing is equal to Kc. So we can rewrite this as Kc. Kp is equal to Kc. But keep in mind, we have RT part in this equation. So here, earlier we saw in the numerator and the denominator when we had RT to specific power. Since they are multiplying, the powers were added. Over here we again have RT in both the numerator and the denominator, but this is a division. So therefore, when the bases are the same, when you are having a division, the powers are reduced from one another. So we can write this as RC to the power, actually this power belongs to both RT, both R and T, bear with me, it's RT. This power belongs to both R and T, not just to T. So when you are writing this, you have to first write C plus D, and since A and B are dividing this term in the numerator, you have to write minus A plus B. So students, this is the relationship between Kp and Kc. Kp is equal to Kc RT, we said delta N. Now delta N is essentially the difference between the addition of reactant or addition of product stoichiometric coefficient minus the reactant stoichiometric coefficient. So we write here product stoichiometric coefficients minus the reactant stoichiometric coefficients, right? So delta N is going to be referred to as the difference between the product and reactant stoichiometric coefficients. So delta N is the difference between product and reactant stoichiometric coefficients. So this is the relationship between Kp and Kc, and you can even define what N is, or else you can leave it this way as well, but this equation is more streamlined. So this is the relationship between Kp and Kc in this particular equilibrium. Right, students. So now we have discussed this question. We can move on to the next. 3 moles of ethanoic acid and 13 moles of methanol was allowed to reach an equilibrium at a specific temperature in the presence of concentrated sulfuric acid. So we will highlight the important details. 3 moles of ethanoic and 13 moles of methanol. Right. And sulfuric acid is used as a catalyst. Through this reaction, 2.8 moles of ester was produced. So we see the amount of ester that is produced is 2.8 moles. And then we have to calculate the Kc value for this equilibrium. First of all, let's write this equilibrium. Let's write this equilibrium. Or let's write the equation for this equilibrium. We have ethanol, CH3, sorry, ethanoic acid, not ethanol, CH3COOH, right? This is reacting with methanol, CH3OH, and this turns into methyl ethanoate, CH3 COOCH3, methyl ethanoate, and water. Now, at this point, we have to write down the initial number of moles that they have given us as well. So, we write it down. Over here, if we write initial amount, basically in moles. So, when it comes to ethanoic acid, we are given 3 moles. When it comes to methanol, we are given 13 moles. Do we have any moles of ester in the beginning, these products in the beginning? No. And then we can write the change that is taking place, right? Change in amounts. Or we can basically say the number of moles that has reacted and produced, right? Number of moles of reactants that have reacted and number of moles of products that have been produced. So over here, the number of moles of reactants that are reacted can easily be found out by observing how many moles are produced, because we don't have the information about how many moles are reacted. Instead, they have given us the number of moles of the ester that is produced, and that happens to be 2.8. Now, since we know initially we didn't have any amount of this ester or water, and we know they are reacted and produced in 1:1 ratio, if this many ester moles are produced, we can say the same number of moles of water is also produced. And to produce this many moles of ester, we have to ask ourselves how many moles of each of these reactants have to react. And to answer that question, you can take a look at the balanced equation here. They are reacting in 1:1 ratio, producing one of these products. So the product ester to ethanoic acid ratio is 1:1. That means to produce one of these products, one of these carboxylic acids should get reacted. That means out of the 3 moles over here, 2.8 moles reacted. 2.8 moles reacted. And since they are reacting in 1:1 ratio, here also 2.8 moles reacted. So these are the number of moles that actually undergo some change. You can see these reactant moles are reacted. So that's why we introduce the negative sign over here to indicate that they get used up and turn into products. And since they are reacting in 1:1 ratio, when 1 mole of this reacts, 1 mole of this is produced. If 10 moles of this reacts, 10 mole of this is produced. So by that argument, you can see when 2.8 moles have reacted, 2.8 moles of this has been produced. So finally, students, we can write the equilibrium number of moles. We can write equilibrium amounts. So this was the initial amount, this much has reacted, so equilibrium amount is going to be 0.2 moles. Here we have been given 13 moles in the beginning, this many moles have reacted, so the difference between the two is 10.2 moles. So 10.2 moles are present at equilibrium. In the beginning we didn't have any of this ester, this many moles of ester is produced, so in the equilibrium we have 2.8 moles. In the beginning we didn't have any water, and when the reaction was proceeding we have produced this many moles of water, so we have 2.8 moles of water here. So these are the equilibrium number of moles of reactants and products. So for this we can write the Kc value, but before we proceed any further we have to find their concentration. So we have to write equilibrium concentration. Equilibrium concentration. So students, now in this question they haven't given us a volume, have they? Have they given us a specific volume? They haven't. So we can say that there is a volume V, or the equilibrium volume is V, right? Let's say this reaction is happening in a beaker like so, and at the final equilibrium we have this much of volume, we'll call this volume V, right? So all of our reactants and products are produced in this volume. So therefore students, we can find the concentration by taking the number of moles over here, right, 0.2, and dividing it by the volume, because number of moles divided by volume is equal to concentration. Over here also we have the same 10.2 divided by volume V, right? So volume is the same for all of these reactants and products. 2.8 divided by V, over here also 2.8 divided by V. So we can write a Kc expression for this. We can write Kc. Kc is equal to concentration of the products, in this case CH3, COOCH3 concentration, multiplied by water's concentration H2O, and divided by concentration of ethanoic acid or acetic acid, and methanol CH3OH. Now we know each of the number of moles here, so we can directly write concentration of these ester and water is equal to 2.8 divided by V. This was the concentration, and each of these concentrations should be raised to its stoichiometric coefficient as a power, but we know the stoichiometric coefficient of each of these is 1, so therefore no powers has been written here because of that reason. And the concentration of water over here, as water is getting produced here as a product in organic medium, so we have to include water. So water's concentration is going to be 2.8 divided by volume divided by the concentration of ester. Concentration of ethanoic acid is 0.2 divided by volume, and then concentration of methanol, which is 10.2 divided by volume. So if you observe over here, although we don't know what V value is, or V is the volume value, although we don't know the volume value over here, this particular expression perfectly cancels off each of these V values. So you can see V over here and V over here cancels off, and V over here and V over here cancels off, producing the final expression like so: 2.8 to the power 2 divided by 2.8 to the power 2 divided by 0.2 multiplied by 10.2. 0.2 multiplied by 10.2. So by solving this equation, we can get to the answer. So let's write the answer now. 3.84. Now keep in mind, students, all of these concentration values have the unit moles per decimeters cube. Since just like the volume cancels off, the units also evenly cancels off. So the final answer here, the final answer over here does not have any units. So the Kc value that you obtain would not have a unit. The answer is going to be 3.84. So this is the information that you need when you are carrying out a reaction like this. And students, it's very important to keep the state symbols right. So we will write them down here. And apart from that, when you're writing your Kc value also, it will be wise to add the state symbols here. Right? So that is how we will approach this question and get to the answer. Keep in mind, when you're attempting a question like this, you will have to have a good idea about the number of moles that get produced and how reactants are getting used up to produce that particular number of moles of product. And you should be able to, by looking at the balanced chemical equation, figure out the stoichiometric ratio between reactants and products, because that is how you will determine the number of moles of reactants that reacted to produce a specific number of moles of product. If you don't have an idea about the stoichiometric ratios, then accurately determining the number of reactants that got used up will be difficult. For example, if you imagine, if the ratio over here, if there was a 2 here, that would mean the ratio between this particular reactant and the product is 2:1. That means you have to have 2 of these moles reacted with one another, this 2 reactants. So 2 of these moles should react to produce 1, right? If there was a 2 here, we don't have a 2, but if I'm just saying so that you have an idea, if the ratio between these two, this reactant and this product is 2:1, that means 2 moles of this should react to produce 1 of this. So at that point, to produce 2.8 moles of the ester, you would need twice as many moles of methanol. So not 2.8, it has to be multiplied by 2. It is going to be 56 or 5.6 moles of ethanol. 5.6 moles of ethanol. So students, that is why I mentioned earlier, stoichiometric ratio is important. So that was for a hypothetical situation where we have a 2 here, but in this case we don't have a 2. In this balanced chemical equation, the stoichiometric ratio between these reactants and this product is 1:1. So that's why when one of these reacts, one of this is produced. That's why when producing 2.8 moles of the ester, we needed to react 2.8 moles of the alcohol and the carboxylic acid. So with that, we can now move on to the next question. So let's take a look at the 4th question here. Consider the equilibrium that is established in a vessel with V decimeters cube volume. So the volume of the vessel is V. And we are having an esterification reaction given here. We have a carboxylic acid reacting with an alcohol to produce ester and water. 1 mole of the carboxylic acid and 1 mole of alcohol was allowed to reach. 1 mole each, very important, was allowed to reach equilibrium at a specific temperature.
if X amount of ester is formed at this temperature, deduce that the Kc value is for this equilibrium is equated to the following expression. So we need to make sure that we are able to deduce that the Kc value is equal to this expression that is given over here. So just like we attempted the previous question, you can attempt this question as well. But in this case, we don't have actual numerical values. Instead, we have these types of symbols or X and Y's to deal with. And then the reaction between the ethanol and ethanoic acid is catalyzed by concentrated sulfuric acid. Describe briefly how you would determine the Kc value for this reaction at room temperature and conditions. So you have to describe how you can determine the Kc value based on your knowledge or based on how you actually conduct the experiment, how you are able to determine the Kc value. So let's take a look at the first part and then we'll move on to the second part. So we have this equation given here, right? And we have to prove that the Kc value comes to this. So we'll rewrite this equation. It will be easier for us that way. So we have RCOOH, carboxylic acid, reacting with R-OH. R-OH. We'll rewrite that part. And these are all in the liquid state. And they turn into be RCOO, R dash, and water. All liquids again. Now keep in mind, students, when this reaction is taking place, from the hydrogen or from the alcohol, the hydrogen group will get removed, and from the carboxylic acid, the OH group will get removed, and those two will form water, and the O end of this alcohol will connect to the carbon over here at the carboxylic acid. And then we can move on to writing the initial number of moles and the reacted amounts, right? So we will first write initial moles or initial amount. So we are given 1 mole of each, 1 mole of this and 1 mole of this. Do we have any of these ester and water given to us? No, we don't have any of the ester or water. So initial amounts is just 1 mole of the carboxylic acid and 1 mole of the alcohol. And then we can write the change in amounts or change in amounts of reactants and products. So this question says that X amount of the ester is produced, indicating that X amount of water is also produced, because if X amount of ester is produced, the same amount of water is produced. And since the stoichiometric ratio between the reactants and products is 1:1, so for example, if you want to figure out how many alcohol molecules react to produce 1 mole of ester, you can see their stoichiometric ratio is 1:1. So when one of these reacts, one of this produced. So for X amount of the ester to be produced, X amount of alcohol should be reacted. X amount of alcohol should be reacted. So when it is reacted, it will be consumed or used up. So that's why we write it as minus. So this is the change that is taking place. And as the alcohol and carboxylic acid reacts in 1:1 ratio, if X amount of alcohol reacts, the same amount of carboxylic acid will also react. So that is the number of moles of the reactants and products that got reacted. And then we can finally write the equilibrium number of moles, right? We can
we can write equilibrium number of moles. Now, when you're writing equilibrium amounts, you can see initially we had 1 mole of the carboxylic acid, X amount reacted. So, initial amount minus the reacted amount is the equilibrium amount. So, we have over here initial amount is 1, reacted amount is X, so 1 minus X. Over here is also the same situation, 1 minus X. And when it comes to the ester, initially we have 0 amount of ester and then X amount of ester is produced. So 0 plus X is X itself. Here also the same, 0 plus X is X itself. And then we can proceed to writing their concentrations. Since the volume is V, we can write equilibrium concentration. Equilibrium concentrations are equal to, we have the number of moles 1 minus X divided by volume. Here also the same, 1 minus X divided by volume. And apart from that, here we have X divided by volume, here X divided by volume. So these are the equilibrium number of, earlier that what we found was equilibrium number of moles, and right now what we found was equilibrium concentrations of reactants and products. And we can write the Kc value now. Kc expression is equal to product concentrations raised to their stoichiometric coefficients as powers. So we have product concentration RCOO R dash, which is the ester, right? This time we have to include the state symbols very clearly, multiplied by the water that is produced, water concentration, divided by reactant concentrations. We have RCOOH. Again, we have liquid multiplied by the alcohol R dash OH. R dash OH concentration. So we have written expressions for each of their concentrations. So the answer would be, now the product concentrations are given here, X divided by volume multiplied by X divided by volume, because you can see these two concentrations are the same, X divided by V. And the reactant concentrations are 1 minus X divided by V, 1 minus X divided by V, 1 minus X, 1 minus X divided by V. Over here also 1 minus X divided by. Now just like in the previous example, or just like in the previous question we discussed, over here you can see the volumes. Although we don't know the volume value, we know these volumes are the same. So the volume over here can be cancelled off with the volume below the line. So this is the numerator volume. We have a denominator also, we have the same value, so we can cancel them off, and this we can be cancelled off over here with this V. And this results in the formation of, and this results in the following expression: X to the power 2 divided by 1 minus X to the power 2. So this is our Kc value. This is our Kc value. So we have now proven that this is the value that we can obtain for Kc. So let's take a look at the question. The question asks us to derive that this is the Kc expression, and we have effectively derived the Kc expression as mentioned in the question. So students, this is how you would get to the answer for a question of that sort. So let's move on to the next question now. The reaction between ethanol and ethanoic acid is catalyzed by concentrated sulfuric acid. Describe how you would determine the Kc value for this reaction at room temperature and pressure conditions. Now, ethanol and ethanoic acid is basically a carboxylic acid and an alcohol. So we can write down CH3 COOH. This is ethanoic acid reacting with ethanol. CH3 CH2 OH. This is the alcohol. And students, when they react, they will form the ester. You should be able to name the ester also. Ethyl ethanoate, CH3 COO CH2 CH3. Apart from that, you will also form water. Now, if we start, now I will not derive the Kc equation as I have already done that in the previous instance, but I will go over this. Now, imagine you have measured and obtained exactly 1 mole of each of the carboxylic acid and the alcohol. So 1 mole of this and 1 mole of this. And initially we don't have any moles of this. And then once we react them, let's say X amount of the product is formed. So we can say after the reaction is carried out, X amount of the carboxylic acid and X amount of the alcohol is reacted, producing X amount of ester and X amount of water. And the equilibrium number of moles at that point would be, we can write in the same color, 1 minus X over here, 1 minus X over here. And these values are going to be X as itself. Now students, we know what we are going to be doing from here onwards. So if you already have gotten to this point, you know you can derive a Kc expression for this equation. Actually, since this is acidification reaction, and even in the previous question, we have done the same type of reaction. This is also acidification. Here, this was a general reaction written for acidification, but in the next question that we looked at, we have specific carboxylic acids and specific alcohols used, but the general theory applies. So if you write a Kc value, you will see instead of these arbitrary values we have, arbitrary symbols we have over here, we will have very specific esters, carboxylic acids and alcohols substituted into the same equation. If you start with 1 mole of the reactants of each, you are going to end up with this Kc expression. So the Kc expression for the reaction we have written over here is the same. So the Kc expression here is the same. We can write Kc is equal to X to the power 2 divided by 1 minus X to the power 2. It's the same as the Kc expression we derived earlier. So at this point, you have to figure out how am I going to find the Kc value. To find the Kc value, you either have to know the X value or the 1 minus X value. One of the two should be known so that you can find the other. So students, a good way of doing this experiment is to take known or 1 mole of each of these, right? 1 mole of each of these, carboxylic acid and ester, 1 mole of carboxylic. So we can take 1 mole of carboxylic acid and 1 mole of alcohol, not ester, 1 mole of alcohol. and then students, you can react them at room temperature. So in order to react them, we have to add the sulfuric acid as well. So when you're adding sulfuric acid, don't add any amount. You have to add a specific number of moles of sulfuric acid. So you can measure a specific volume, and you have to make sure that you know the exact number of moles of sulfuric acid that you added into the mixture. Since sulfuric acid is a catalyst here, it is not going to be used up, so it will be present in the medium. So students, after you have carried out this reaction, imagine you have carried this reaction out. You initially started with, right? Let's say you have your alcohol and your ester, right? So we have, initially we have, let's say R, we will use R here, RCOOH. This is our carboxylic acid. We have exactly 1 mole of it in here, and we have our alcohol, ROH, exactly 1 mole, right? And to this, we will add a known amount of sulfuric acid. Known amount. Now students, after this reaches an equilibrium, we are going to titrate this. We can take a small portion of it and titrate, or we can titrate the entire solution with the use of sodium hydroxide. So when the sodium hydroxide is added, students, it is initially going to react with the sulfuric acid that is present in the medium. But we know exactly the number of moles of sulfuric acid we added into the medium. So we know, if you know the concentration of sodium hydroxide, we know the exact amount of sodium hydroxide that is going to react with the sulfuric acid in the medium. And then, if you continue this titration, the remaining amount of the carboxylic acid will react with the sodium hydroxide added. So the remaining amount is this. You can find this out then. Right, students? So that is how we are going to be doing this titration. And keep in mind, when you are trying to titrate this carboxylic acid, you might ask, or you might wonder, won't the equilibrium shift in the reverse direction and try to produce more and more of this while breaking down the ester? Yes, that is possible. So that is why when you are carrying out this titration, we are going to be lowering the temperature to about 10 degrees Celsius. So this reaction will be sufficiently slowed down, and it won't necessarily come back in enough speed to produce more and more of this as we react it with our sodium hydroxide. So understand, students? Now students, when we lower the temperature to 10 degrees Celsius, we can be sure that the reverse reaction is not taking place. So only the carboxylic acid that was present in the medium at that point will get reacted with the sodium hydroxide that is added. So over here, what we are going to first do is we react these together, and then we are going to titrate the solution. We are going to titrate the solution with sodium hydroxide. We are going to titrate the solution with sodium hydroxide at around 10 degrees Celsius. The reason for using this temperature is to make sure that the equilibrium will not shift to the left, producing more and more carboxylic acid. We need to only find the carboxylic acid that was present in the medium that has not turned into the ester. So we are going to be using NaOH. Concentration is known, right? We have to take sodium hydroxide with known concentration, and this is the equilibrium mixture. So equilibrium mixture that we have over here was obtained at 25 degrees Celsius. So the equilibrium was established at 25 degrees and we are decreasing the temperature rapidly and then only carrying out this titration. At that point, if you have any remaining carboxylic acid, it will also react and we can find the amount of carboxylic acid that was reacted as we know the sulfuric acid that was added. So the total amount of sodium hydroxide that is spent over here can be used to calculate the number of moles of sodium hydroxide that was spent in this titration. And out of the total number of moles of sodium hydroxide that was spent, we know how many moles of sodium hydroxide was spent on sulfuric acid. Why? Because we know the exact number of moles of sulfuric acid that was added into the medium. So therefore, students, if you reduce that number of moles from the number of moles of total number of moles of sodium hydroxide that was added, you get the number of moles of sodium hydroxide that was spent on titrating with the carboxylic acid that was present in the medium. So if you write over here, you can write total NaOH spent on titration is equal to number of moles of sulfuric in the medium plus number of moles of the carboxylic acid remaining in the medium. Remaining means after the main reaction. So this is the number of moles that is referred to as 1 minus x, right? This is the number of moles that is referred to as 1 minus x. So you can find that number of moles. And after that, students, if you know 1 minus x, now if you have found a value for 1 minus x, right, then you know we introduce only 1 mole, you know 1 minus x value, then you can figure out what the x value is, right? So basically at that point, you know all of these numbers of moles. If you find out this value through the knowledge that we have about the initial number of moles, we can find out what the x amount is. So based on that, we know the value of x as well as the value of 1 minus x. So if you know the value of x and if you know the value of 1 minus x, we can find out the Kc value. So students, this is how we find the Kc value. So let's go over the steps again. We will first take 1 mole of alcohol and 1 mole of carboxylic acid and a known number of moles of sulfuric mixed together in a known volume, and we will allow it to reach an equilibrium. Afterwards, we are going to titrate this mixture by initially bringing the temperature of the mixture quickly to 10 degrees Celsius so that the reverse reaction won't take place when we are carrying out the reaction, right? And we are going to titrate this mixture now with sodium hydroxide with a known concentration. So sodium hydroxide initially will react with the sulfuric acid we added into the medium, and after all the sulfuric acid is finished, it will react with the carboxylic acid present in the medium. And as the carboxylic acid gets used up, the reverse reaction will not take place because we have lowered the temperature to 10 degrees Celsius. At a lower temperature, the rate of the reaction will be so slow, we can consider that the reverse reaction is not taking place. So therefore, the carboxylic acid that gets used up here is the carboxylic acid that was remaining in the medium at equilibrium that we obtained at 25 degrees Celsius. So students, this way you can find out the carboxylic acid number of moles, because When we know the number of sodium hydroxide moles that was used up, we know a part of it went into being titrated with sulfuric acid. And since we know the sulfuric acid number of moles, we can calculate the number of moles of sodium hydroxide that was spent on that. And then the remaining number of sodium hydroxide moles were spent on reacting with this carboxylic acid that was remaining in the medium. So remaining number of carboxylic acid is equal to 1 minus x. So we have found out the 1 minus x terms value, and since we know that we introduce only 1 mole into the medium, we can find out what the x value is. So when you know x and 1 minus x, using those two values, we can find out the Kc value. So this is how we can do this question, students. So with this question, we can conclude our question discussion. So by now, I hope you have developed a good enough understanding of how to attempt equilibrium related questions. And I hope you have developed a good understanding about the Fe3 plus thiocyanate equilibrium as well. We have conducted a practical on this. So I hope you have a good understanding of that equilibrium as well. So students, with that, we can conclude today's experiment. I will see you again in the next experiment.